What is up, everybody? How are we doing today? Welcome. Toby's Sheet Metal Tips and Tricks 2023. I'm just giving a moment here to make sure that I got all the audio sounding good, looking good. Got my little monitoring computer over here, so I think that everything sounds good and looks good. But of course, as always, please let me know if anything ever sounds out of line. But it sounds pretty good to me. I'm looking like 5x5 on my end. So what is up, everybody? So good to see everybody here. Let me see if I can get another chat window open here so that I can give you guys the appropriate shout outs here. Let's see here. I think we want this to be this one. Oh yeah, that's a good one. Here we go. The whole crew is here today. This is awesome, man. So what's up? Welcome. Charles says I sound great. Thank you, Charles. Appreciate that. Niku is here. What's up? Mohammed is here. Welcome. We got Charles here. Shout out from Naphide. What's up? Thanks a lot to the crew at Naphide for joining us today. Great to see you in here today. Robert G is here. What's up? Thanks for joining us for these sheet metal tips and tricks. And Ivan is here. Hello, Ivan and Richard Hill, old friends of the show. Francis Martin is here. Welcome. Rigoberto Ramirez. What's up, Rigo? Thanks a lot for joining us today. Great to see you in here. Ben says it's Toby time. Yeah, let's go. And Stefan is here. What's up, Stefan? Thanks for joining us. Nuno, great to see you in here, old friend. Been great catching up with you a little bit. It's been cool communicating with you on the interwebs. Robbie is here. What's up, Robbie? Thanks for joining us. Says keep up the awesome work. Oh God, what am I doing? I'm clicking in the wrong spots. Not there, somewhere else. Here we go. Fixed, no problem. Johnny is here. Hello from Denmark. Hello, Johnny. Thanks for joining us. And let's see, we got Charles and Robert G is here. 5x5 from Texas. Okay, excellent. That's what I needed to hear to get the morning started. So welcome you guys to Toby's Tips and Tricks 2023 Sheet Metal. Achilles is here. What's up, Achilles? Thank you for joining us. Great to see you here. Welcome to Toby's Tips and Tricks 2023 for Sheet Metal. This is going to be a presentation that will help you understand some fundamentals of sheet metal, kind of some underlying good foundations. I would probably call this somewhere between beginners and intermediate for sheet metal. It's really designed to make sure that people get off on the right foot, but there's going to be plenty of tips in here that even if you've been using sheet metal for years, you're going to learn some stuff that you didn't know before, and that's going to help you get out of jams in the future. A lot of what I do on my channel is to try to help people get out of jams in the future, and so that's a big part of how this presentation is structured today. So overall, I would probably give it a label of somewhere between beginner and intermediate, but I'm willing to bet that even if you're an advanced user, you're going to learn a lot from this presentation. So let's get into it here. We're going to talk about our digital 3D CAD users group. Maybe monthly. I don't know. I'm thinking about doing this monthly. I did this last month. I did it on Toby's Tips and Tricks, mainly on sketching. It went really well. This month, maybe, we'll see what happens here. Maybe we'll do it again this month. Maybe we'll do it again next month. I don't know. Maybe we'll make this a monthly thing. For now, we're going to see how it goes. But if we do it again, it'll probably be the same day of the week, the last Tuesday of the month, April 25th. Maybe I'll do it on surfacing or tips for sweeps. I don't know. We'll figure it out. That's in the future. Let's focus on what we're talking about today. Toby's Tips and Tricks for Sheet Metal 2023. This is going to go for about 90 minutes, and it's going to be in 3 parts. Maybe we'll take a short break in the middle. And last time I said we were going to go for 75 minutes, and we ended up going for 3 hours last month. So I hope that it's not quite that same marathon, but it's really up to you. It's up to whatever kind of questions you guys ask me, and I'm happy to answer any questions that come in. That's the cool thing about doing live stream and about having audience interactivity. So just let me know if you guys have any questions, and I will try to answer them. And I'm happy to deviate a little from the stated plan in order to answer those questions. So please feel free to fire those questions into the chat. What's up, Taylor O from Calgary? Welcome. So the agenda for this presentation is we're going to start out by talking about the 3 different techniques for creating sheet metal. That's the insert bends technique, the base flange and friends technique, and the convert to sheet metal technique. Then we're going to get into understanding some little bit of history lesson here, some sheet metal template information, and then we're going to finish up by talking about the flat pattern feature. We're going to dissect that feature and talk a little bit about some specific settings you want to look out for, common settings that I've seen people maybe get incorrect. The goals of this presentation are, our first goal here is going to be to make sure that you understand the different ways to approach sheet metal and the different circumstances that affect which technique you should be using from those 3 techniques that I mentioned a moment ago. The second goal here, this one's for Taylor from Calgary. The second goal is to understand the best way to make a flat pattern configuration and the key options found in the flat pattern feature. And the third goal is that you will learn at least one additional tip or trick during this presentation. So when we get to the end of this 90-minute presentation, hopefully you will have achieved these 3 goals and maybe even more. Maybe we'll do some bonus time or something. We'll get you some more goals as well. Ivan recognizes this goal. He's seen one of these, once or twice before. These are our goals for the presentation. All right, cool. So now, I'm sure you're wondering after seeing that slide of, what you're going to get out of this presentation. You're probably wondering, well, how can I support you, Toby? How can I give back to you for this wonderful presentation? Well, there's some easy ways you can give back. The first and the easiest way is to just hit like. It looks like there are 32 people watching right now. Looks like there's 22 likes on this video. So I'm going to go over to my monitoring computer and make sure that I like this. The first and the easiest thing you can do is just make sure that you like this. If you're watching it live or if you're watching the recording, be sure to hit that like button. Let's get those numbers to match. The second thing that you can do is you can subscribe to this channel so that you know when I'm coming out with more content, and so we can try to achieve our subscription goal for the year. It's all about setting goals and trying to get there. And yeah, you know what, Nuno, you're right. That does look like a one-up, kind of like a one-up free man icon. So that's funny. I never really noticed that before. And the third goal. What's up, Sally? How you doing? Welcome to the party. Very old friend of mine, Sally. Not old as in age, old as in I've known her for a long time. So welcome. And then another thing that you can do to support is you can make sure if you're watching this, especially if you're watching the recording of this presentation, you can make sure that you add a comment. So even if you get done watching the presentation today, certainly let's get a lot of chat activity going, but when it's over, if you can go back and leave a comment and let me know what you liked about the presentation, that really helps as well. And finally, if you can share and reshare, if you want to take a screen capture of what we're doing today, if you see something really cool, grab a screen capture, throw it up on your social media, include a link back to this video and say, hey, this was really cool. We did a really cool tips and tricks today. I learned something I didn't know before. Here's a screen capture of what I learned. And you share that out and you include a link back to my channel, back to this video. It is very, very helpful. What's up, Marty? Welcome. What's up, Adam? Thanks for joining us today. Welcome. And of course, I have to give a huge thank you to the sponsor of today's live stream, SolidBox. SolidBox has really been helping out my channel all throughout this past year. An amazing team of people over there at SolidBox. And what SolidBox does is they specialize in putting together computers for professional CAD or CAM engineers. So if you're out there, if you're a CAD or a CAM user and you need to get some new computers, or if your team is in the market to get some new computers, you want to be sure to check out mysolidbox.com. Because what they'll do on the website is they will go through and make sure that you spec out a computer that's appropriate for the type of work that you're doing, which is very, very helpful. But beyond that, they actually get the computer in-house in their shop before they send it to you. And they make tweaks to Windows and make tweaks to the BIOS to make sure that all that great hardware that you spec'd out is actually being properly utilized. You don't want to get a brand new computer and then immediately have to go to IT and say, hey, I need you to adjust this setting in the BIOS, or I need you to adjust the way the CPU is working so that I can really take full advantage for SolidWorks. Then IT is going to say, did you make a ticket? And you're going to say, no, I didn't think I needed one because I already had a ticket when I ordered this computer. And then they're going to say, well, you need a ticket. I can't do anything without a ticket. And you guys know how that goes. You've been there, I'm sure. So you want to make sure that as soon as you get that computer out of the shipping container, it just goes right onto your desk and you're immediately immediately able to start, you know, being a professional CAD or CAM engineer. You want that thing to be optimized and ready to go. And that's what the team at SolidBox does. And beyond that, just on a little bit of a personal note, the team at SolidBox has always been super, super supportive of the SolidWorks users community, really the entire CAD users community. In fact, last year they won the SolidWorks Users Group Network Sponsor of the Year for all the efforts they made in 2022 to kind of re-kickstart the live in-person users group. The SolidBox team really believes in these live in-person users groups, which this is a virtual in-person users group. It's kind of right on the line, but they did a lot to put together a tour of in-person live users groups. And so it's just, it's always good to know companies out there that are supporting the SolidWorks community. If you want to support them back, the next time you're in the market for a computer, be sure to check out mysolidbox.com. Awesome team over there. And with that, one last thing I just want to say is if you guys are in the chat and you see something that you really like, be sure to put a 1 in the chat. A 1 in the chat is kind of like a way of clapping or applauding. If you guys want to try it right now, just to make sure that everybody can hear me and that the audio is good, put a 1 in the chat. You just type the number 1 and press enter. If it's a big deal, if it's like a standing ovation, you can spam a bunch of 1s and then you can press enter. But putting a 1 in the chat is kind of my way of getting feedback from you. If you see something you like, if I'm on the right track, if I show you something that you're really enjoying, you put a 1 in the chat. That lets me know that that I'm on the right track. All right, and I'm seeing all these 1s come in, so thank you so much. Nuno, Adam, Charles, Anti-Venom, BJH. Anti-Venom, what's up? Barry, what's up? I haven't said hi to either of you guys yet. Welcome, welcome. And EA, what's up, EA? And Rigo, and Dan, and Taylor, and Sally, and Nico. Thank you, thank you, thank you so much. That is awesome. My 1 button is about to die in this presentation. Yeah, I'll bet this is going to be a good one for sure. All right, and Achilles and Stefan are with us as well. Awesome, awesome, awesome. And Richard Hill, what's up? And Robert T. All right, cool. All right, let's get into it here. The 3 techniques for creating sheet metal, the first part of our agenda for today's presentation. So there are 3 techniques for creating sheet metal in SolidWorks. And the first of those techniques is the oldest, and it's what's called insert bends. This was introduced in the software way back in 1997. And the idea of insert bends is when you get into the software, you create a model which is all thin features, all uniform wall thickness. So you create a model with uniform wall thickness. Then you click this button that says insert bends, or you go into the insert pull-down menu and you choose bends. That's how we did it in the old days. And once you choose insert bends, you're going to need to specify what are called ripped parameters. You're going to need to specify what's called a fixed face. And then you are going to be able to unfold that model into a flat pattern. And this is how we did things in the old days. So in the old days, what we would do is we would start a new part here in SolidWorks. We would, let me flip over to my keyboard cam. So we would start a new part in SolidWorks. Let's say I'm going to make this in millimeters here. And we would go to our front plane, begin a sketch, orient the view. And once we begin the sketch and orient the view, we could create some geometry like a rectangle here. I'll make this rectangle 60 by 120. And then I will extrude that out to a depth of 110. And then I will select this face here, begin a sketch, and I'll sketch a rectangle like so with, let's say, 25 by 50. And S key extrude cut, and then I'm going to single click on this vertex here at the end of the model, and then I'm going to right mouse button to finish, and there we go. And so now we're ready to take this geometry and turn it into uniform wall thickness. I'm going to make this a wall thickness of 3 millimeters, and I'm going to choose to remove this face and this face. So now we've created a model which has uniform wall thickness, and we're ready to turn this into a sheet metal design. Now up at the top here, if we do a right mouse button on one of these tabs, we can turn on and off different tabs. So I go tabs here, I can turn off weldments, tabs here, I can turn off sheet metal. And if we right mouse button on one of these tabs, we can go to tabs and we can turn on sheet metal. And that's where we want to go to access all of our sheet metal tools. And once we get in here and access our sheet metal tools, we can see that we've got a tool up here called Insert Bends. It's all the way at the end. It's like they just took it and moved it all the way over here to the end, this Insert Bends command. But it is one of the OGs, one of the original tools that were available in SolidWorks for sheet metal. Well, not original in SolidWorks, but 1997-ish. The Insert Bends command became available for sheet metal users. And so the way that this works is we choose Insert Bends, and then we have to choose what's called a fixed face or edge. So I'm going to choose this face here. That's my fixed face or edge. And then we have to specify what's called a bend radius. Now, the basic rule for bend radius is the bend radius should never be smaller than the wall thickness. So that's just a general rule in sheet metal. You don't want the bend radius to ever be smaller than the wall thickness of your sheet metal design. If the bend radius is smaller, you start running into issues where either the material will rip or break, or the tooling can actually break if you make the radius too small. So you really don't ever want that bend radius to be too small. You always want it to be as big as or larger than the sheet metal wall thickness. So for this first example, I'm going to make it the same. The wall thickness was 3, so I'm going to make the bend radius 3 as well. Now, I still have a little bit of a problem here with this design. This model cannot unfold. What I want is this rear face here. So if you imagine this rear face comes up and over and up like this, I want this whole rear face to kind of bend down to the back. So that bends down to the back. This face here bends over. This face here bends over. But right now, I can't unfold that. Let's see here. Very hard to hear you. Music is play over your voice. Alrighty, thank you. Let's dial that music down a little bit. I don't think we need the music to be that loud today. Oh, you know what? It's coming through the same channel. Interesting. Okay, a little bit of a new setup here. So thank you very much for that, Marty. Let me just dial this down over here. And if you could, please, let me know if that is good. I don't mind it being a little bit quiet in the background for that music, but I don't want it to be too loud. So, Marty, I very much appreciate that. Why is the music louder than the voice? Is this a me issue? All right, well, I doubt that it's you. I think it's probably me. Music is low now. Okay, cool. All right, thank you very much, Marty. Appreciate that. Yep, guys, put a 1 in the chat if that sounds much better. If everybody can hear me now, good. And if anything needs to be a little bit louder, I can make further adjustments, but hopefully that is good. Jeremy says that's what we needed, baby. Okay, cool. Thank you, guys. A little bit of a new setup today. I got a better quality mic, but still learning how to route some of the stuff through. Charles says it's 0.5. Okay, thank you. Thank you, Charles. Yeah, if you guys have any suggestions, if anything could be louder, quieter, you just let me know, and I will make those adjustments. So when it comes to creating this sheet metal using this old school technique of insert bends, we have to get in here and we have to create what are called rips on this model. So the first thing that we did, just to review, is we created a model with uniform wall thickness of 3. Next, we came up here to our sheet metal tools. We clicked insert bends. Next, we clicked on this face here for our fixed face. And then we were able to get in here and create what's called, or then we were able to get in here and create what's called the default bend radius. We always want that bend radius to be equal to or greater than our material thickness. So the material here is 3, so a radius of 3 is fine, but we don't want to go any lower than a radius of 3. Then we're going to come down here to what's called the rip parameters, and we're going to use these rip parameters to specify that we need to separate these two edges, or these two faces along this edge. So there needs to be a rip here, otherwise this thing isn't going to be able to bend backwards. And there needs to be a rip here, and here, and here. And so the way we do that is we go down into the rip parameters and we click on this edge here, and that allows us to rip that edge as we turn this thing into a sheet metal design. We hit the green check mark and it says auto relief cuts were made for 1 or more bend. Okay, that's fine. That's basically saying that down here, in order to bend both of these at the corner here and here, we needed to clear out some of that geometry to make that bend feasible. And we can see that we now have a sheet metal design which can be flattened. Now, although we don't really use this technique that much anymore, we don't use the insert bends functionality that much anymore, there are some key areas where we use this technique, and that's why I wanted to start the presentation today by talking about this technique. And one of those areas is when we need to flatten a cone or a cylinder. So a very common question that comes up in the world of sheet metal is, how do I take some geometry like this, and we'll make this a thin feature, how do I take some geometry like this and unroll it? So I'll make that a radius of 4. How do we take something like this and unroll it? Well, the answer to that question is we first create some kind of a seam. So usually what I do is I do a triangle with an angle that starts at the center. That way, both of those edges are perpendicular to the center of the model for the unrolling process. And then after we create that thin feature cylinder with a seam, we can again use this command, insert bends. And when we choose insert bends, we can say that this is going to be our edge for the bend. The radius in this case actually doesn't matter, and I'll explain why that is in just a moment. But we're going to insert this bend here, and we're going to hit the green check mark. And now we can choose flatten, and we can take that cylinder and we can unroll it. So this is a very common question that we get in the world of sheet metal. And one answer to that question is, if you've got a cylinder already and you want to turn it into a flat, you can use this old school command, insert bends. But there's some other good places that we can use insert bends as well. And one of those places is we can use insert bends when we are working in imported geometry. So when I went through, I created this. Remember, we did our initial sketch. We created this geometry here. Well, I did use some shortcuts there to create that geometry, and those shortcuts are available on my YouTube channel. If you want to check out my YouTube channel, I did some S key functionality. I did some auto dimensions. I did some end condition shortcuts. That's all on the same YouTube channel in the playlist called Power Moves. And also something new that I'm working on. This is just being announced right now. It's kind of being rolled out in beta here. Is TooTallToby.com/tips. If you go to TooTallToby.com/tips, you'll see that I'm also taking some of these power moves and organizing them and tagging them and making them a little easier to search. It's not totally revised at this point, still kind of in beta. So some of the links that are up top there aren't exactly working the way I want them to, but by the end of the week, I should have it pretty much dialed in, and you should be able to search using these links up top. So just another place that you can go to get some really valuable tips to save some time. And I used some of those tips when I was using, when I was creating that initial model. Now, another place, so we showed how to take that geometry and how to unfold that geometry, but another topic that's really important in the world of sheet metal is the topic of bend deformation. And what bend deformation in the flat pattern means is that when you create sheet metal and when you actually bend sheet metal, you get deformation in two locations. You get deformation on the inside of the bend in the form of compression. So this section here in the inside of the bend gets kind of crinkled up. And you get deformation on the outside of the bend in the form of stretch. So this here gets kind of stretched out as we go along the outside of the bend. So you get deformation in two different locations. You have this kind of neutral axis that's going through the middle of the sheet metal, but that neutral axis also gets a little bit deformed as you actually do the bending of the sheet metal design. So when we do the bending of geometry, the flat that you end up with is not really the same as this inside radius arc length. So if you were to take the length from point A to point B there, and if you were to take the length from point A to point B here, that's really not going to be the correct length in the flat either. Both of those edges are being deformed. And so if we were to look at this in SolidWorks and we were to create a sheet metal part like what we see here, and we were to measure that outside edge, it might come out to something like 287.98. And if we take that inside edge and we measure that, the full inside edge here, that might come out to like 275.42. But the result in the flat is not either of those values. The result in the flat is 281.70. And the reason why, again, is because there's deformation taking place in that bend region. Now, we can see this in SolidWorks if we just take a look at the flat pattern, if we just do, some quick measurements. So if I, for example, select this edge here and I take this curve and I create an arc on it, and then I begin a smart dimension and I pick the arc and the endpoint and the other endpoint of the arc, SolidWorks tells me what that arc length is. It's 4.71. But then if I go into a flat and I click on that edge, this is an option here that I'm going to teach you guys about a little bit later. Save that discussion for later. And I click on this edge, I can see that down here, the length is 7.07. Oops, I think I did my arc. I think I did that arc. I might have done a chord distance there, huh? Instead of an arc length. Let me go back and do that again. Oh, that looks like arc length. Huh. Wonder what the outside one is. Let's see here. Convert. And select this. And this. And this. Oh, there we go. Okay, yeah, it does make sense. So the inside one has an arc length of 4.71. The outside one has an arc length of 9.42. But when I flip this thing into the flat, when we go into the flat there, we end up with a dimension that's kind of in between those two. So we go into the flat here, we look at this edge, and we can see that this edge is 7.07 millimeters. So what we're seeing there is we're seeing that phenomenon where the inside bend is compressing and the outside bend is expanding. And what this means is that if we were to give this design to somebody and ask them to form this out on the machines that they have out on the shop floor, there's a little bit of trial and error to figure out what does the flat pattern actually need to be. And this trial and error is something that has been worked out over the years by machinists and by press brake operators, and this is something that you'll often see. I used to work at a company. We had a chart like this on the wall that would tell us what the bend allowance or what the bend deduction is. And so in the case of bend deduction, what I would do is I would measure to the sharp corner. So maybe this is 3 inches here going down to the sharp corner. This is 3.5 inches coming across here. And then I would look at the chart and I would say, what's the gauge of that material and what's the radius of the bend? And then I would be able to figure out how much I needed to subtract from that total distance. So if the total distance was 3 plus 3.5, so 7.5, I might need to subtract 0.238 from that 7.5 in order to calculate what the flat length should be. These numbers aren't exactly one-to-one for this example, but the concept is that for a long time you had to do this by hand, and it required a lot of trial and error to figure out what exactly would work on different machines. And it's different on different machines, it's different on different materials, it's different with different bend radius, it's different with different material thicknesses. So all these things factor into calculating what the distance is in the flat. Now, SolidWorks does offer a really valuable tool to help you with this in a very simple format, and it's what's called a K-factor. So if we were to take this geometry here, let's make this 3 by 3.5, similar to the example that I showed a moment ago on that print. I'll make this for construction, and now I'm going to extrude this. I'm going to just do this as a thin feature extrusion with a wall thickness of 0.25. So I'm going to say thin feature here, 0.25, and I'm going to say this is going to come out to 3 inches. There we go. And then I'm going to use the old school sheet metal tool, insert bends. So I pick this face here, I pick this bend here. And then we've got this section called bend allowance. So the bend allowance is using a K-factor, and the K-factor is 0.5. Well, in my experience, if you use a K-factor of about 0.333, that usually works out pretty well. If you don't have any idea what your K-factor should be, then you could just make it 0.33333, and that would be fine. But of course, again, this requires a lot of trial and error and a lot of communication with the people on the shop floor to get it correct. I'll make my bend radius here 0.25 to match the material thickness, although if you're bending 1/4 inch, it doesn't quite work out that well, but whatever, we'll talk about that later. And so I'm going to hit the green check mark here. And so now we've got our flat pattern, which we can examine. Here's what it looks like in the flat. Here's what it looks like in the form. And if we were to select this face and begin a sketch and then select this tangency here, or I won't make a sketch. I'll just measure the tangency. So right mouse button, select tangency. We can see that the total length there is 8.785. Total length is 8.785. But if we put this thing into the flat, we can see that the length of all of those edges is 9.047. So what does a K-factor of 0.33333 represent? It represents going 1/3 of the way through the material thickness. So in the straight here, the straight distance is just going to be the same. It's going to be straight. But if I right mouse button, select tangency here, and I do an offset entity, and I do 0.3333 times 0.250 for the wall thickness, and then if I was to measure that entire path, that'll give me that 9.047, whatever the distance was in the flat. So if I did a select chain here, and after I do a select chain, if I do an evaluate measure, we can see that that distance is 9.047, and that 9.047 is the same distance that we are getting in the flat. So if I exit the sketch here and I go back to the flat pattern, and I pick on these edges here, there's our 9.047. So the lesson there is whenever you're looking at a K-factor in the definition of a sheet metal, so when we go in here to edit feature and we say bend allowance and we look at the K-factor, if we're doing a K-factor here of 0.33333, what we're saying is that we're going 1/3 of the way into the material in the bend regions. So we're going from here to here. This is, 0.3333 times 0.25, whatever the wall thickness is. And that's really useful because that means that K-factor will work on a 90-degree bend, but it'll also work on a non-90-degree bend. Bend allowance and bend deduction are more of like a static value. It only really works on 90-degree bends or on a specific angled bend. It also means that K-factor will work regardless of what the material thickness is because it's a ratio through the material thickness. So K-factor is usually where people start when they're trying to learn how to use sheet metal because it's a very versatile bend deduction calculation tool or bend allowance calculation tool. But there are many other types of bend allowance. You can do what's called bend allowance, where you measure to the tangency point and then you add some material. You can do what's called bend deduction, where you measure to the sharps and then you remove some material. These are the examples, kind of like what we see on this chart here, where you have a chart up on the wall and you use that chart to calculate it manually. Well, you can just embed that directly in SolidWorks. You can create what's called a bend table, or you can even create what's called a sheet metal gauge table that incorporates some of this information. You can do advanced bend calculations where the calculation is this up to a certain material thickness and then it changes to this, or the calculation is this up to a certain angle and then it changes to this. So there's a lot of tools that you can use to get this correct so that anytime you create a sheet metal design, you can take it out to the shop floor and you can be confident that the flat pattern is going to be correct. Ultimately, that's what we're trying to avoid here, right? We don't want to create a flat pattern that is going to be incorrect when we go out to the shop floor. Now, let me show you a common example of how that can happen. The distance here along this flat region is supposed to be 0.524. That's what the distance is when we measure this thing at 1/3 of the way through the material using K-factor. 0.524 is what that length is supposed to be in the bend. But what if instead of using K-factor, I said that I wanted to use a bend allowance or a bend deduction? Let's say I wanted to use a bend deduction of 90 thou. And so I hit the green check mark. And now this thing looks good in the form, but when I go into the flat and I measure that length there, now it's coming out at 900 thou. So now it's coming out at 0.91. So that's my, oh, I'm sorry. No, I was correct the first time, 90 thou. So that's my calculation of this distance, which is supposed to be 0.547, according to a K-factor of 1/3 of the way through. Now this distance here is measuring at 0.91. Well, what this ultimately means is that I'm going to be making these parts that are way too long when I cut them in the flat. So we're going to cut these in the flat. We're going to take them out to the shop. The shop's going to, spec off and probably measure from this end and create the first bend and then create the second bend, or they'll put it into a die and have the die create those bends at the same time. And then they're going to find that either one of the legs is too long and one of them is the correct length, or they're going to find that both of those legs are too long when they put it back into the formed shape. So this is, one of the perils of working with sheet metal is understanding that you can make the flat pattern an incorrect length, and that's going to be a problem for everybody downstream. You're going to ultimately be making scrap parts, and nobody wants to be the person who was responsible for making scrap parts. That is not a fun day to be in your supervisor's office. So the way that we avoid making incorrect flat parts is we work with the team who's out there operating the presses. We work with that team. We try to get a good understanding of what is the appropriate bend deformation calculation. Can we get away with just using K-factor? If so, what's the appropriate ratio into the material? Does it change depending on what material we're using? Does it change depending on what thickness we're using? These are all really important discussions to have with the team out on the floor. And most likely these discussions have already been had before you were there. But now at least you can enter into these discussions and you can understand a little bit more about what's happening in this world of bend deformation. The material is getting compressed in the corners and it's getting stretched in the corners. And so the flat is not exactly the same as measuring all of the inside edges or all of the outside edges. Shout out to Garrett in the chat. Thanks a lot for the super chat, Garrett. Appreciate it. Appreciate the support. Glad that you are enjoying this presentation. And Adam is here, says +1 to work with the team. Yes, very, very important. Remember, your name is on each feature so your coworkers will know if you are the sheet metal noob. Yes, that's a great point. Yeah, any feature that you create. In fact, I'm going to talk about this a little bit later, but it's a really good point. If somebody makes these parts and if you make these parts and then later on you say, oh, I didn't do that, I didn't make those parts. Well, whenever anybody looks at the SolidWorks feature in the tree, they can go to feature properties and they can see, well, somebody was on a computer called TooTallToby. And, they were using a username called TooTallToby, so they needed to, they were the ones who did this. It's going to be hard for you to deny that it was you. That's the point. And let's see here. What else we got in the chat here? What's up? What's up? Okay. I don't think I missed any other questions. If I missed any other questions, let me know. Oh, Achilles here is pointing out something really good. Achilles is saying that in our workshop, we use a K factor of 0.47. Okay, so that's awesome. So, and I'm sure, or at least I'm willing to bet that that was determined by going back and forth with the shop floor a little bit and figuring out like what is the best K factor, what gets us closest to the correct length in the blank. Because you cut this material in the blank and then you form it up, so it needs to be correct in the flat. Okay, great question. Adam says, insert bends versus convert to sheet metal. Yep, we're going to talk about convert to sheet metal. That is the third of these techniques that we're going to go through during this first section of the presentation. So great question. And I think I got all the other questions. Achilles confirming here, yes, we've done a lot of testing to find out what the right K factor was. Yeah, I'll bet. I've been in those conversations too with the shop floor, so I know it for sure, for sure. Okay, and let's see here. And I think there was another question. Oh, Niku asked, how do you draw the live red lines? It's called Zoom It. You can look it up. It's called Zoom It. I'm going to make a video on Zoom It someday. I get that question a lot, so I'll definitely make a video on that at some point. Okay, cool. Cool, cool, cool. And Rigo gives me a 1 in the chat. All right, thank you very much, Rigo. Appreciate it. All right, so that is that's basically all I wanted to say about the first of those methods. Oh, actually, there is one more thing I wanted to say about that. So this, again, this first method, create the model with uniform wall thickness, insert bends, declare face, fixed face for rips, and then examine the flat pattern. Now, this can be really, really useful when you're working with imported geometry. So if you've got a step file and you import that step file, you can use this insert bends command to flatten that step file, and it can be very, very useful, and it can be a great time saver. And what's cool is that this works with both sharp edges and it works with round edges. So I'm going to talk about the sharp edges first, and then we'll talk about the round edges and how that's kind of a unique case. So let's go over here. Let's get into our step file that we're going to be using for this. And we're going to bring in this full table here as a step file. I do have 3D interconnect disabled. I talked about that in my live presentation last month. So if you want to learn about 3D interconnect, take a look at that presentation from last month. But that way this thing opens up as its own standalone. And we can see here that once we get this model into its own window, we've got uniform wall thickness. Now, there's a couple ways that you can determine whether or not you've got uniform wall thickness. You can eyeball this thing up. You know, you could click on this edge here, and then you can look down in the status bar, and you can see that that edge has a length of 3 millimeters. And then you could, you know, click on this edge, and you can see that that has a length of 3 millimeters as well. There's also an evaluate tool. If you go to evaluate, there's a thickness analysis. Normally, we would use thickness analysis for plastics design to make sure that the entire injected molded part has the correct wall thickness, but you could also use it here. So you could say calculate, and you could let SolidWorks go through and determine whether or not everything is in fact the same wall thickness. So thickness analysis is another tool that we can use to make sure that everything is correct. Whoops, I specified the range too high. Make that 3. Calculate. All regions of the model have a thickness greater than or equal to the target thickness. And then if we said show thick regions, you could also do it that way, and that way you'll get like a nice gradient. But in this case, the scale down at the bottom here is showing me that everything is 3. Take a sip of my coffee while. All right, cool. So we're getting the right results down here. Everything is 3. We are good. We are good. Everything is the same wall thickness. If it's not the same wall thickness, I'll show you what will happen if it's not the same wall thickness. But at this point, I can choose the sheet metal command of insert bends. And by the way, quick question for the chat. If the wall thickness is 3, what should I make the bend radius? So a quick question for the chat. We'll see who can answer that one first. We did our thickness analysis. The thickness analysis confirmed that the wall thickness is 3. So what do you think the bend radius should be in the when I go to the insert bends command? Because these are all sharp right now, right? I need to make this, I need to tell SolidWorks what this bend radius should be. And Taylor gets in there in the chat first with 3 millimeters. That is correct. Daniel answering a little more accurately. It should be equal to or greater than 3. That is correct. That is correct. Excellent answers. Anti-Venom and Rigo getting in the mix as well. That is correct. So when I go to insert bends, I'm going to pick this face as my fixed face. And then over here in the bend radius, I'm going to say I want the bend radius to be 3. And I'm going to hit the green check mark. And now I have a sheet metal part that can be flattened, that can be added to a drawing, and that can be ultimately manufactured in our shop. So if you have geometry that you import from a step file, and it all has uniform wall thickness, and it has sharp corners, well, guess what? You're in a good spot to use insert bends. That's another good spot to use insert bends. Now, what if it didn't have uniform wall thickness? So let's say I go to this face here, and I say insert face move, and I make this face a little bit thicker. I'll make this face 5 instead of 3. So I'll make that one 5. And then I'm going to do the same thing on this end, but I'm going to do it with 2 faces just so you see the difference. So I'll make this one here 5 as well. So these are 5 now. So now I'm going to go to insert bends, and SolidWorks is going to look at the thickness of the face that I select for the fixed face, and it's going to say, that's what the wall thickness is going to be, 3 millimeters. And so when I hit the green check mark, I get an error or a warning over here in the tree, a warning. But more importantly, the geometry on the faces that was non-uniform just disappears. So that's not good, right? That's not gonna be manufacturing the part correctly if some of those faces are missing. So that's what happens if the wall thickness is not uniform. So the wall thickness needs to be uniform, and if it's got sharp edges, that's fine. You can create the sheet metal using insert bends, and you can have those models in a state that you can flatten them and then send them out to the shop to get them manufactured. What about if you receive a model and that model has pre-existing rounded edges in it? Well, this is an interesting thing about the insert bends command. The way the insert bends command works is that if there's sharp geometry on your model, so I'm going to come over here 1 inch, and then I'm going to come up 2 inches, and then I'm going to come over 1.5 inches, and then I'm going to create a round here like so at 1.25 inch radius like that. And I'm going to turn that into a thin feature, so boss extrude with thin feature, and I'll give this thing a wall thickness of 90 thou. So thin feature with a wall thickness of 90 thou. And then I'm going to create a sheet metal feature using insert bends, a tool we've been talking about so far, the first of the 3 tools that we're going to be learning about during this first section of the presentation. So I go insert bends, and when I choose insert bends and I pick this face here, I'm going to say that I want to have a bend radius of either 90 thou or greater. We have 1/8 inch tooling in the shop, so I'm going to use 1/8 inch for my bend radius here, and I'm going to hit the green check mark. Now this location here where it was sharp, I got a radius of 0.125, radius 0.125. This location here where it was sharp, radius of 0.125. But this radius here where it started out as a curved face, well, SolidWorks leaves that area alone. And because of what we learned about K-factor, that's okay. Because with K-factor, what SolidWorks will do is it'll go, 1/3 of the way into the material, and it'll use that for the flat length for that geometry. So that's okay. That's the cool thing about K-factor, is that you can use K-factor on non-uniform bend radii and bend angles. So I still get a pretty accurate flat pattern here using K-factor, and SolidWorks was able to take those sharp corners and turn them into rounds. That's good to know about, because when you're working with imported geometry, and that imported geometry comes in as a sheet metal design, but the sheet metal design has bends already in it, well, these bends are going to remain their current radius, and unfortunately, that radius is 1.5. And the reason I say that's unfortunate is because we measured the thickness before. It was 3 millimeters, and this shelf also has a thickness of 3 millimeters, so our bend radius is too small. It's too small for that material. We need that bend radius to be larger. So let's go to the insert bends command. We're going to pick this face. We're going to say we want that bend radius to be 5 millimeters. 5 millimeters for that bend radius. And we'll come down here. Right now it's 1.5. So we should see that grow, right? We should see that get a lot bigger. So we hit the green check mark, and it says, first of all, it says the bend process cannot be completed. Oh, you know what? Maybe I didn't pick a fixed face correctly. Let me try that again. This face here, insert bends, 5 millimeters, that face, green check mark. That's interesting. This is not what I expected to have happen. Wonder if this model came in bad. Hold on, let me do an import diagnostics. Maybe it has bad face. Try this again. Insert bends, this, 5 millimeters. That's interesting. Wonder if that 5 millimeters is just too large for something else that's happening that it's seeing. I didn't, when I tested this, I did it at 3, so 3 should work fine. Or not. Okay. Process bend 4. Interesting. But regardless, we can see here that we ended up with this radius not changing. So this radius here is still 1.5. I know it's erroring, but it doesn't affect the point that I'm making. The point that I'm making here is that this radius started out at 1.5. I said I wanted it to be 5, and it's still 1.5. So why is that? Because when the model came in with the tangent faces pre-configured at 1.5 millimeters. And so that's what SolidWorks is going to use. So when we go into the flat pattern is going to use that as though it's the 1.5 millimeters. And that's why it's going to, be problematic. So this really should have unfolded, though. I don't know why. I'm a little perplexed as to why that didn't. I'm just because I'm an engineer and I don't like when things don't work the way that they, the way that I know that they worked in practice. I'm just gonna kind of give myself a fresh start here. So let me bring this in again. So bring in this. Everything comes in good. Bring in this. No feature recognition. We could do an import diagnostics if that face is really the problem, but I don't think it is. And then we're going to say that we want to take this and do an insert bends. Here's the problem. So this is, okay, this is good to know too. So for some reason, this, the bend deduction setting, maybe it's the bend deduction setting that I set before, was turned on. And, this can be very frustrating too. So I'm actually glad this happened. This gives us a great teaching opportunity. So the bend deduction option was still turned on, and that should have been K factor. So if we change that to K factor, make that 0.333, let's make this 5 millimeters, and we hit the green check mark, and no problem. The model turned into a sheet metal. I didn't get any errors, and I can flatten this model, but the radius of 1.5 is still being enforced here. Now, any new features that I create, if I take this edge, for example, and I make a new feature coming off of there, that's going to have that nice big radius of 5 millimeters that we want. But those pre-existing bends are going to be problematic. And so if this ever happens to you, if you ever receive a model from someone and the model has the incorrect bend radius, or you don't have that tooling in-house, you're going to want to use the delete face command to clean up that model before you do the sheet metal. So you can see over here in the tree, I did a Control-Z, Control-Z, Control-Z. I got rid of all the sheet metal stuff and just went back to where I originally started. And now I'm going to do this as a 1/4 model because I want to save time. So I'm going to do insert cut with surface and pick one of the center planes and cut this model in half. And then I'm going to do insert cut with surface. And I'm going to pick, again, one of the center planes and cut this model in half. And then I'm going to use the command insert face delete. And I'm going to delete all these faces that the vendor gave me when I received this model, or the customer gave me. So the customer, maybe they made this model in a different CAD package, and they were like, hey, we already made it sheet metal. Can you work with sheet metal? And I say, yeah, no problem. Send it over. I'll flatten it. But then I receive it, and their radii are all, non-workable. Well, I do the command insert face delete. I go around and I pick all 8 of those faces, and I'm going to use delete and patch here. I hit the green check mark. That turns them all into sharp edges. And now I'm going to pick this face and use insert bends. And I'm going to say I want that to be a radius of 5 millimeters. Hit the green check mark. Now you see when I pick on this edge here, it's got a radius of 5 millimeters. That's what I wanted. This is a model that can be flattened, so now we can manufacture this in-house for the customer. And now I can finish up by going to Features Mirror, and I'm going to mirror about this face using this bodies to mirror. Then I'll press Enter on my keyboard to repeat the last command, and I'm going to say this face is going to be mirrored, and this is going to be the body to mirror. And so now I've got a nice set of sheet metal geometry that I can flatten, that I can send out to the shop floor, that has the correct radius for the tooling that we have in-house, even though the customer gave it to us with those incorrect radii on the part. So, okay, Rigo's giving me 1 in the chat. Adam giving me a 1, 1, 1, 1, 1. Okay, cool. You guys like that? Yeah, that is definitely a good workaround if you ever receive imported geometry from another CAD system. That can definitely save you a lot of headache. And again, even though it was annoying in the live stream, I'm actually very glad that that issue came up with the bend deduction, bend allowance. You really got to keep an eye on that. It should be stored in your template, and it should work, but sometimes these things don't actually work the way they're supposed to, and you just really got to be aware that when you're creating sheet metal, there's this section here, it's kind of like collapsed, called bend allowance. Make sure that that's on the correct bend allowance for what you're trying to do. In my case, what was happening was that it was set to an unsolvable bend deduction value. SolidWorks just couldn't solve for that value that I had in there, and instead I wanted to be the more, what's the word I'm looking for? The tool that can be used in a lot more different scenarios. Amicable is almost the word I was thinking of there. The more amicable tool of K-factor. So it's such an amicable fella, this K-factor. You can use that K-factor in a lot of different scenarios, and it will generally give you a good result. Cool. All right. Awesome. Well, thank you. Thank you for the kind words, Charles. And thank you for the 1111111, Daniel. Appreciate it. Appreciate it. Appreciate it. All right, cool. Let's go back to our overview of what we're trying to cover today. And I think that's going to bring us to the end of the 3 methods of sheet metal, part 1, insert bends. This is what the notes would look like. I'm a habitual note taker. So if you're taking notes on this section of the presentation, this is what I would write down. The insert bends command is more of an old school tool. It kind of came out in 1997, 1998. It must have uniform wall thickness. So you create a model with uniform wall thickness. And bend deformation is very important to understand for every sheet metal application, not just insert bends, but for all the techniques I'm going to teach you today. The flat pattern length will be different from the form length. And you can also see here that the insert bends command can be very useful when you're working with imported models. Dan Anderson says, game-changing tips. Thank you. My pleasure, Dan. Thank you. Thank you. All righty. Cool. So if you guys want to grab a screen capture of that, if you're taking notes, I mean, of course, the recording is going to be available as soon as we're done today. But if I was taking notes, this is pretty much what my notes would look like. Let's move on now and talk about method 2, the base flange and friends method. This is a method that was added to SolidWorks a little bit later in time. And with this method, what you do is you start out with a thin feature sketch. So you start out by sketching some basic geometry in SolidWorks, and then you immediately turn that geometry into a sheet metal design. So you click the base flange tab command, and after you use the base flange tab command, what you do is you declare the wall thickness and the bend radius. So the base flange tab command, you say, I want this to have a wall thickness of 4. I want to have a bend radius of 6. I want it to have a K factor of 0.33333. So last time when we did this, we just did a regular thin feature, boss base extrude. But this time when we're doing it, we're actually creating it as thin feature right out of the gate. And so you can see here that now, when we're done creating that initial feature, we have the ability to create additional sheet metal features. And there's lots of cool additional sheet metal features that you can create when you're using base flange and friends. So for example, if I were to create a new part here and go front plane, begin a sketch, orient my view, and create a rectangle with a height of 60 and a width of 130, I can take this point and make it a midpoint and get rid of that lower edge. And then I can choose to turn that into the sheet metal. Very first command up here, the base flange and tab. This is, I would consider this more of like the de facto standard when you're beginning a new part. This is probably how you're going to do most of your sheet metal when you're creating new parts. You're going to use the base flange tab command. So I'm going to go base flange tab, and I'm going to bring that out. And as I bring that out, I'm going to say that it has a sheet metal wall thickness of 3 and a sheet metal bend radius of 6. So there's my base flange tab, or I can make that maybe a little smaller, make it a radius of 4. So wall thickness of 3, radius of 4. Now, whenever you're creating your sheet metal designs, you want to keep in mind that you've got this option for material inside or material outside. And so this just depends on, you know, what you're designing around. If this dimension of 130 represents the width of a circuit board and you're creating a casing to go over top of that circuit board, well, then you'd want the material to be outside. If this is a little pocket that goes into another vessel and the width of that other vessel is like 131, then you'd want the material to go on the inside. So it just depends on what you're designing for. That's how you determine whether this is material inside or material outside. Now, once you've created that initial shape using base flange tab, of course, you can flatten this geometry. You can always go into the flatten command. But what we can also do with base flange tab is we can click on this edge on the back here, and then we can choose some of these other cool tools like edge flange. And with edge flange, what I can do is I can bring an edge flange down. I can even click on a vertex here and have that edge flange go directly to that vertex. So I can click on a vertex here. And similar to what I mentioned a moment ago, the base flange tab command is going to have some options for the flange position. So the material could be on the inside, or the material could be on the outside, or the entire bend could be on the outside. Now, if you create this with the bend on the outside, that looks okay, but then you're gonna need to do some cleanup in the corner here. You're gonna need to pull these corners together. And so another tool that's available in the base flange and friends command is the close corner command. So I could click on this corner here and bring these two corners together. I could declare that I want that to be an overlap or an underlap, or I could just have them butt together at the corner. I'll make it an overlap. I think that'll look really good. And I can do the same thing on the other side. So I could do a closed corner here from sheet metal, and I could say that I want to have this, this rear section overlap the same way. The rear section kind of completely overlaps there. That's pretty cool. We could do an edge flange that is flush to the top of the table. So we could go edge flange here. And like I said a moment ago, instead of this being the bend sticking out on the bottom here, you can control what's called your flange position. This is very important in sheet metal, flange position, this section down here, because what this does is it lets you control where that sheet metal is going to end up relative to the original material. And in this case, I'm going to say that the flange position is flush, or material inside, so that this new edge flange that I'm creating will be flush to the top of the table. You can also edit the flange profile, which is the sketch that's used to drive the flange. So I can move this over a little bit here. I can move this over a little bit here. And now at this point, I'm going to get what's called auto relief. So I get some relief here, because you're not going to be able to create a bend that just tears this material here. You need to have some kind of a gap, not only side to side, but also an additional gap above and beyond the bend. So if we finish this, you can see what that gap looks like. So we've got this gap coming across here horizontally, and we've got this gap here as well going up. Well, that gap is defined by what's called a relief ratio, typically. It's down here at the bottom. You've got this custom relief type. And normally what you use is what's called a relief ratio, and the ratio is 0.5. And so what that 0.5 means is that the material that is removed, both horizontally and vertical, in this case from the tangency point of the flange, is 1/2 of the material thickness. So if I click on this edge here, we can see that measures at 1.5. And if I was to click on this edge here, it also measures at 1.5, because that is 1/2 of the material thickness. It's got a relief ratio of 0.5. Of course, if you had some kind of a unique flange, or if you needed it to be a very specific amount, or if you have like a tool in-house that helps with that, you can uncheck that relief ratio option, and then you could make this a set distance. So the width of that is going to be 3 millimeters, and the distance beyond the tangency point of the flange is going to be 5 millimeters. Give myself a little bit more room to bend that thing out. When you're working with that flange, you can also, in that edit flange profile command, you can change the overall shape of the flange. It doesn't have to remain rectangular like what we see here. So for example, I could delete that top edge and then get in there and create a round like so. And I could even put a nested contour in there, like a hole that I need to mount to for this flange. This is all functionality that lands in this category of the second of our sheet metal tools, the base flange and friends commands. So the base flange tab is how you get started, but then he's got all these friends here that hang out with him up in this toolbar, and they're all really useful. Another one that's really useful is the miter flange command. So I can pick this edge here and choose miter flange. And then what happens is a new sketch plane is created, and on that sketch plane I can create geometry that I basically sweep along the edges of the sheet metal. So when I exit that sketch, you can see that the miter flange allows me to take that geometry and sweep it all along the edges of the sheet metal and create a miter flange very quickly, very easily there in the world of sheet metal. And one of my favorite tools that's available in sheet metal is what's called the jog command in sheet metal. So let me create another flange over here on this side. I'm going to do edge flange to begin with and bring an edge flange out here. I'll make it flush with the bottom of the material, and then I will create an edit to this flange. I'll make it a little bit thinner in this direction, a little bit thinner in this direction, and I will create another full round out here on the end. So just go into the line command, come back, touch the end point, and then come around with a line like so. And I'll make another nested contour just for good measure. Now, there's two really cool tools that work very similarly. The first one is the sketched bend command. So I can select this face here, begin a sketch, and I can sketch a line that comes across like this at an angle. And then I can use that line for what's called a sketched bend command in sheet metal. And what you do with the sketch bend command is you pick on one side of the line or the other, and wherever you pick, the sheet metal geometry remains stationary, and then that line is used for a bend. So let's say I wanted to make that 45 degrees. Pretty cool stuff there. You can use the sketch bend to create a bend like so. The other tool that we've got, I'm going to Control Z to undo that. The other tool that we've got that's really useful in the world of sheet metal is what's called a jog command. So once again, I'm going to create a line here that runs across the sheet metal. This time I'm going to actually dimension that line from the edge of the sheet metal at 30 millimeters. And then I'm going to go to the sheet metal command and I'm going to choose jog. And what jog does is once again asks you to pick on one side or the other of the line, but then it allows you to take that sheet metal tab that I've created and bend it in 2 places. So the jog command is really, really useful in sheet metal. And what's cool is that you've got this option over here for the jog command. Fixed projected length. Now, the way that you can visualize fixed projected length is if you look at that tab from a view where you're looking dead on at it, you'll notice that that hole is still in the same position. That's because I'm taking the original jog and I'm just projecting it straight up. And so in essence, what I'm doing is I'm adding material. This is all additional material right here along that angle. But you don't have to do that. If you know what it's supposed to be in the flat, you can uncheck that option. And now you can see that it's no longer directly in line with the original hole. Because now I'm taking that flat and I'm bending it and then I'm bending it again. So fixed projected length versus not fixed projected length, very important to understand in the world of jog. The other thing that we can do with jog that's really handy is we could say fixed projected length, and then we could say we want that to go up to another surface. So we want the jog to come up so that it is flush with the top of the material, hit the green check mark, and now we've got this really cool sheet metal enclosure that we can bolt in from the top here, and we can bolt in from the bottom here, and it's just gonna slide right into that little enclosure that it's supposed to nest into. So those are just some of the tools that are available in Base, Flange, and Friends. You can learn a lot about these in sheet metal training if you take the sheet metal training class, or if you go through the help and you go through the tutorials, or even if you just one at a time go through each of these. You can learn a lot about these Base, Flange, and Tab tools. But the Base, Flange, and Tab is another really useful tool in SolidWorks. If you were creating something brand new like this model here, you would almost certainly use Base, Flange, and Tab to create something like this. You might, a model like this, you might start out by creating the geometry, looking at this thing from this side. So maybe your first sketch would look something like this, and you would do Base, Flange, Tab. Me personally, I would probably only do half of the model. So I would take that Base, Flange, Tab and I would just extrude it over in this direction. So just half of that 190, create that Base, Flange, Tab, and now you're ready to create an edge flange. So you would create this edge flange that's coming up here. That's going to give you this kind of triangular shape. So you'd create an edge flange that would start out looking like this, and you would edit the flange sketch and remove this extra material here. Now you've got your first edge flange, and then you would do another edge flange, and you would create this geometry over here. And once again, you'd edit the sketch to pull it up from the bottom of that edge. So Base, Flange, and Tab, very, very useful when you're working in SolidWorks. It's a really, really cool bit of functionality. It's the second of the 3 methods of sheet metal. These are the notes that I would take. Base, Flange, and Friends, the most popular method of creating a new model in sheet metal, used when creating sheet metal, used when creating new parts. And there are many tools like edge flange, miter flange, jog, hem, flat pattern, and the flat pattern length is different from the form length. That note is always the same, right? How are we doing with the audio? Is the audio good? Let's see. Hopefully it's good. Looks like it might be a little quiet. Hopefully it's good. Yeah. I'm not hearing any music coming through, but I think that's probably okay. Sound is good. All good. Okay, cool. All right, excellent. Excellent. Okay, well, let's move on then to the third method of creating sheet metal. Convert to sheet metal. Convert to sheet metal is a very useful tool when you've got complicated angles on your models. It can really, really make your life easy. It's like the secret weapon in the world of sheet metal. And so in the case of this vertical conveyor feeder, what we've got is a very complicated set of geometry that we need to attempt to work with for sheet metal. This layout, we can see has an angle down here at the bottom, an angle down here at the bottom. And so we might need to start out by sketching on a plane that's at that angle. So let's go to our top plane, begin a sketch, orient our view. I'm going to take this and convert it. And then I'm going to use that sketch line. Actually, I didn't need to convert that to create a new plane. So we'll create a new plane relative to the top plane at an angle of 8 degrees. And I'll flip that offset for that angle. And then I'm going to create a new sketch on that surface, which is going to take this sketch and convert it. So I'll take all this geometry here and do a convert entities. And then I'm going to turn that into my sheet metal base flange tab. Now, if you don't have any edges that are popping up from that thing, you just specify the sheet metal wall thickness and the K factor info. But there's nothing that's, there's no edges that are bending off of this right now. So that gives me my initial sheet metal shape using base flange and friends technique. And now I need to create an edge that's coming up from this. So an edge flange here that's coming up from this. And it needs to go up to a certain height, but it also needs to be kind of tapered itself. So here you can see that I can adjust the angle of that flange, but it needs to be adjusted a little beyond the normal angle. And then it also needs to terminate exactly at the top, which, you know, we could just say that in the end, we're going to cut this thing off just for sake of illustration. I think you're still going to see how difficult this gets and how quickly it becomes difficult. So now I'm going to create another edge flange coming off of here. So an edge flange that's going to come up like so. And now I need to change the angle of this because this needs to taper out as well. So this is going to come out. I think it comes out at 5 degrees is what that vertical conveyor system is using, or 4 degrees. So this is going to be coming tapering out as well. But then I also need to edit this flange profile and change this angle so that the angle matches with that other one. And you can see that I kind of got it close there, but it's going to take a lot for me to get those to match up perfectly. And then I'm going to need to repeat that here with this one as well. So another edge flange coming up here like so. But again, that needs to be tapered out. And again, that needs to match up with that geometry, which is, you know, not the easiest to get matched up. Sometimes if you edit flange profile, you can maybe get in there and do like a collinear relationship and, you know, see if you get lucky. Let's see if I can make that collinear. Nope, it errored. When I tried to do collinear, it errored. So I didn't get lucky. So, you know, this is the point of me going through and doing this on screen here is just to show you that this is not easy to get geometry to line up when you've got a lot of funky angles that need to all match up together. Not easy to do in sheet metal. At least it's not easy to do with base flange and friends. But it is easy if you know how to use what's called convert to sheet metal. So I'm going to do file reload. That basically dumps what's in RAM and reloads this file from the fixed disk. So now I'm back to where I started. And I'm going to take this shape here, and I'm going to do an extrusion of this shape. So features, extrude. I'm going to take this up to this surface here, and I'm going to say that that is going to draft outward at 4 degrees. So draft outward at 4 degrees, like so. And then I'm going to take that top surface, and I'm going to do a convert entities and an extrude up to this surface here. That's just going to go up straight. So it starts out flanging out, and then it becomes straight up at the top. And then I'm going to go to my front or my right plane, begin a sketch, and I'm going to take this geometry here and do a cut extrude through all in both directions and lop off the bottom of that part. That's pretty easy to do in SolidWorks. That's extrude and that's cut extrude. Not too much fanciness going on with that geometry in SolidWorks. Extrude and cut extrude to create that basic geometry. But now we're going to turn this into sheet metal. And when we turn this into sheet metal, we're going to use the second command here called convert to sheet metal. And what convert to sheet metal lets you do, and this is really cool, convert to sheet metal lets you pick a face of the model, any face of the model, and it lets you type in a value for the wall thickness of that face. So I'm going to make this 0.25, and the bend radius of that face. So I'll make that 0.25 as well. We can do reverse thickness so that that thickness is going to the inside, and we're going to uncheck keep body for now, but I'll talk about that more in a couple of minutes. We're going to hit the green check mark, and SolidWorks just took that face and turned it into sheet metal. Now, that in and of itself is not all that exciting, but what we're going to do, I'm going to Control Z here, is we're going to take this one step further now. We're going to go convert to sheet metal. I'm going to pick this face, 0.25, 0.25. We're going to do a reverse reverse direction for the wall thickness, make sure the wall thickness is going in. And then we are going to come down here into this section where it says bend edges, and we're going to choose this edge here. Bend edges, we're going to choose this edge here. And this is where this gets really, really cool. Because what SolidWorks does is it ignores all the rest of the geometry of the model, and it just takes my flat face, which I said I wanted to be sheet metal, and this edge that I selected, and it turns those two into sheet metal features. So it took this face as a flat face, it applied a bend with an inside bend radius, and then applied this face going up here as a flange that can be flattened, which is so cool. Now, I explained that to you using, bite-sized steps just so you can understand how convert to sheet metal works. Now I'm going to Control Z and I'm going to do the whole thing to show you how powerful this is. So I start out here with a solid model. This is a nice solid model, totally solid. I'm going to say convert to sheet metal. This is going to be my face that is fixed. So my fixed face parameter, 0.25, 0.25 for the bend radius. I'm going to pick this edge here to bend, and I'm going to pick this edge up here to bend, where it bends around up at the top. I'm going to pick this edge here to bend, and notice it's automatically creating a gap right here along this purple line. It's creating a gap because I can't have a bend here, right? It can't be bending up from the bottom and bend there, so it has to rip there. And I'm going to select this edge here to bend, this edge here to bend, and this edge here to bend. I'm going to select this edge here to bend, and this edge here to bend. And finally, I'm going to select this edge here and this edge here. SolidWorks will now ignore any faces that, we're not connected to with bends. I hit the green check mark, and boom, there is my sheet metal vertical conveyor system. Now it's got a taper on the bottom face. It's flaring out at 4 degrees as it goes up these walls. All these walls are coming together so they can be welded together once it gets bent, and it's sheet metal so it can be flattened and it can be reformed. So I can actually take that out to the plasma cutter and cut that blank. And that is pretty darn cool. And that is the power of learning how to use convert to sheet metal. Anything that you can draw up as a solid, as long as it's not too crazy, swoopy, lofty, but compound angles on flat faces that, need to fit into an old building that's not exactly square or plumb, and you need to put a new cap on top of something, and it's, all these weird, funky angles, different elevations. As long as you can draw it up as a solid, you can convert it to sheet metal, and you can start working with your sheet metal tools. And then once you use to convert to sheet metal, then you're able to start using all your base flange and friends commands. So like edge flange, I could put a 2-inch edge flange coming off of this back edge here. So I'm going to make that at 2 inches. And then I can just go around and pick all these top edges and get them all at once. So I could put a 2-inch edge flange sticking out on all edges here, put some holes on that so I can, mount this thing to whatever it's mounting to. And again, this can all at any point be flattened and can be reformed. So this is the power of convert to sheet metal. Convert to sheet metal is just an epic tool, and one that anybody who's getting serious about sheet metal should learn how to use. And that is the third of the 3 techniques for creating sheet metal. You start out by creating your solid geometry. It could also be a surface. It doesn't have to be a solid. It could also be a surface. You use the command convert to sheet metal. You pick a face to be fixed, and then you go around and you pick all your edges for where your bends are going to take place. And then finally, you create additional sheet metal features, your cuts, your edge flanges, miter flanges, hems, anything you need to do from the base flange and friends, you can add in here to the convert to sheet metal as well. This can also be used for non-uniform wall thickness. And the reason why is because the convert to sheet metal functionality does not care about the existing wall thickness. So what I mean by that is if we had an imported step file here, like this part here, that has non-uniform wall thickness. So you can see here, this is non-uniform wall thickness. This is non-uniform wall thickness here. Well, when we do the insert bends command, when we do the insert bends command, everything needs to be uniform. When we do the convert to sheet metal command, what's the first thing that we do? We pick this face, and then we tell SolidWorks how thick the sheet metal is supposed to be. So SolidWorks doesn't care what the original wall thickness was. It doesn't care that this was 3. You want to make this 5 millimeters? Do it. You want to make it 2 millimeters? Do it. SolidWorks doesn't care what the original thickness was. And that means that even though this is non-uniform here, if we make this 3 with a bend radius of 5, even though this is non-uniform here, I can still pick this edge and I can still pick this edge here. And SolidWorks is going to allow me to turn that into the sheet metal design, and that can be flattened. So when you're importing non-uniform wall thickness, that can be another place where you can really take advantage of the convert to sheet metal functionality to allow yourself to kind of get around that, that bad model that somebody else sent you. And finally, taking this to the next level, the vertical conveyor feeder number 2, the second part of this, when we go to this next level, what we can do is we can use the keep body option. And what this allows us to do is create multi-body sheet metal designs using the convert to sheet metal functionality. And once we create these multiple bodies, we can actually take these and put them into a drawing using the model view command and then using select bodies from the model view command. So what this looks like in SolidWorks is, just like in the last example, we start out with a solid. So I'm going to bring this in here. This is a solid part here. Now, just for disclosure, a little bit of behind the curtain information, I created this part with a plain carbon steel appearance, and then I colored the body green. And the reason I did that is because when I start converting this to sheet metal, I just want you guys to see the difference in color, the original body versus the sheet metal body. So there's no real magic going on there. I applied a color, and when I applied a color, I said I wanted to apply it to the body. So now that we've got this this part here ready to turn into sheet metal, I'm going to use the convert to sheet metal function, and I'm going to say that I want to convert this. Actually, I'm going to convert this lower face here. Let me start over. I'm going to say that I want to convert to sheet metal, and I want to convert this face here. So I'm going to do convert to sheet metal. I'm going to convert this face. I'm going to make this a, oh crud. I already added sheet metal, so I have a default value here. Let me delete that as well. Okay. Convert to sheet metal, this face here. Okay, there we go. I want to set the default value. So I'll make this 0.125, and I'll make the wall thickness 0.125, the bend radius 0.1875 for the bend radius. And then for my bend edges, I'm going to choose this edge and this edge. And remember, when you're doing anything sheet metal, you always want to be aware of the idea of bend inside, bend outside. I want to make this 0.25 for the wall thickness just to make it a little easier to see. So 0.25, just makes it a little easier to see. So we've got this bend material inside, bend material outside, and it's going to be important to understand which one you're using in order to get the correct results from your sheet metal. So just to show both, I'll bend this to the inside. And then in the property manager here, I'm going to say keep body. That means the green body here, don't delete that body from the tree. Keep that body so I can keep using it. In the previous example, we got rid of that body once we were done converting. But in this example, I'm going to say keep body. And I hit the green check mark, and now I've got a sheet metal body here. You can see now that difference in colors I was talking about earlier, and a solid body here. So now I'm going to do convert to sheet metal, and I'm going to pick this face as my fixed face, and this edge here is my bent edge. And this time I'm going to do reverse thickness so that these two sheet metal bodies, match up. They overlap a little bit. So I'm going to hit the green check mark. I'm going to say keep body. I'm going to hit the green check mark here. That creates my second sheet metal body. So now I've got these two sheet metal bodies and this one solid body, and these two match up perfectly. How awesome is that? From this very easy to create geometry here, a boss extrude, a boss extrude, a boss extrude, a boss extrude, and a fillet. That was it for my original geometry. I was able to create this really cool sheet metal interaction. So let's do it again. So we're going to go convert to sheet metal, and I'm going to pick this face here, and I'm going to say this is a bent edge. And this time I'm going to say this face here is a bent edge, because this is one of these situations where the bend starts out formed. So this face is a bent edge as well. And this is going to be material to the outside again. Hit the keep body once again, hit the green check mark. And then for my final sheet metal here, I'm going to get real ambitious with this top hopper area. I'm going to say convert to sheet metal. I'll pick this face up here, come down to my bent edges. I'm going to bend down and around the corner, and then around the corner up top here, and then down and around the corner up top here, and then down and around the corner up top here, and then down. And since I'm done with the solid now, I'm going to uncheck this option for keep body, and that will get rid of that solid body and just leave me with those 4 sheet metal bodies. So for this sheet metal design, I was able to bend around up at the top, and I was able to get those 4 down at the bottom. I'm not sure why the color scheme changed. Let me say if I keep body. I'm just curious here now. Keep body. Okay, that made it silver, and then I could go into that original solid body and just delete it. Delete the solid body. Oh, nope, still made it green. Okay. We could do a what is it? Control Shift C. Is that how you do it? Control Shift C copies the appearance, and then I could do a paste appearance to that body. So paste appearance to that body. Yeah, Control Shift C is a shortcut to copy appearance. So then I could paste appearance on that body. It doesn't really matter for what we're talking about today, but just like a little, these little things bother me when they don't look perfect. So I try to clean them up as best I can. So now I could go File, Make Drawing from Part, and I'll use the Model Monday Live template. We got to start doing Model Monday Live again. I'm missing it. And then I could bring in this view here of this thing in its assembled state. And then up here at the top of your drawings, you're going to use this option for Model View. And when I use that option for Model View, I'm going to say that I want to select bodies, and then I can just choose one of these bodies, and I can say that I want that body to come in the flat pattern state. So now I've got a view of this thing in the flat pattern just for that body, and then I can just repeat. So I'll pick that part, go here to solid bodies, and then I'm going to pick this solid body. And then over here in the property manager, I'm going to choose the, oops, what happened? Did I misclick escape or something? Feeder, next, select bodies, this body here. Yep, flat pattern. Okay. There we go. And then I can, once again, model view, pick the model that I want to get the view from, click the select bodies button, and I'll pick this one up top here this time, the check mark, and I will, wow, why is that just, like, it's just totally noping me. It's like, nope, sorry, you have to do it twice if you want it to work. That's the trick. That's the old SolidWorks trick. You have to do it twice. And then this one is going to be a flat pattern as well. There we go. There's the flat pattern for that. You can turn these bend notes on and off too. You click on the flat pattern view and just say bend notes if you don't want to see them. And then there's one more body for this thing, right? So model view, next, select bodies, and then I'll rotate this around and get this body here, check mark, and flat pattern. And there we go. So that is the power of learning how to use the sheet metal tool for convert to sheet metal. If you really want to make that a power move, what you're able to do is you're able to go through and create that using a single part as almost like a layout. Complicated angles, very difficult to get that all to work together when you've got compound angles when you're doing traditional base flange and Friends tools, but very easy to do if you can just draw that up as a solid and then use convert to sheet metal. You start with a solid or a surface. The sheet metal features can be added after the conversion. It's great for complex angled parts. It's great for multi-body design. Remember to use keep body. It can be used for imports with non-uniform wall thickness. And of course, as we've been talking about, the flat pattern length is different from the form length. So those are the notes that I would take on that section. And that takes us to the end of section 1. I think this is probably a good time to take a short break, and I know that we're already creeping up on that 90 minutes that we were shooting for the target for this. I think the second half of this presentation is a little bit shorter, but Richard says, GG, thank you, good game from Richard. Appreciate that, Richard. And just a reminder here, we talked earlier about how you can support this presentation. You can make sure you hit that like button, make sure you subscribe, make sure you comment, and of course, make sure you share this presentation. Take a screen capture, you can share it with somebody else, share something you learned and direct them back here. But if you feel like you're getting a lot of value out of this presentation, I like to operate on what I call a value for value proposition. I lifted that term from one of my favorite podcasts, the value for value proposition, which basically says, if you feel like you're getting some value out of this presentation, assign some kind of financial value to that, so some kind of a financial number to how much value you're getting, and then send that value back to me. You can send it to me by going to TooTallToby.com. There's a link right on the main page that says support. You can send me some value, whatever the value is to you. you. Maybe it's $5, maybe it's $100, right? It could be anything in between, but whatever that value is to you, if you're getting value out of these tips and tricks, I'm trying to make a new career here out of this, and so I'm trying to model my new career off of this value for value proposition. You could also do this via what's called Super Chat. So right in YouTube, right down at the bottom of the chat, there's a little $sign. You can use a credit card there, and you can send some Super Chat directly into the chat here for everybody to see. Or if you're watching the recording, there's a similar mechanism called Super Thanks that you can use to send some value back my way. Whatever that value is to you. And I know that not everybody's in a position to send that value back, and if you're not, believe me, I'm very thankful for just a like, a subscribe, a comment. All those things are awesome. But if you are in a position and you do feel like you're getting a lot of value out of this presentation, please feel free to send some value back, just like Auday just did. Thank you so much, Auday. Really, really appreciate it. Very much appreciate it. And Garrett sent in some super chat earlier as well. Thank you, thank you, thank you. Anything you guys can do to support the channel, if you're getting value out of this, feel free to send some value back. And with that, I'll let you guys work on that during the break. Let's take a short break just for a few minutes here. And after our break, we will get back into it and continue with our sheet metal tips and tricks, talking about some history of templates and some flat pattern stuff. I think that section will be a little shorter, probably closer to 30, 40 minutes. I don't think it'll be much longer than that. If you have to go, thank you so much for joining us, but I hope that you'll come back after the break. Oh, yeah. What's up? What's up? What's up, everybody? Thank you so much, Dorigo. Very much appreciate the value for value. Awesome, awesome. Thank you very much. I have to get back to work. Yes, I'm sure. I know we're running a little long. Sometimes we run a little long here. Adam says, fillet in sheet metal tab, understand faces. When you select a face, it recognizes only the corners. Corners only chamfer correct corners versus all the edges. Yeah, that is true. It's also kind of interesting that it knows to, not only to not chamfer the way it would normally chamfer a face or fillet a face, but it also kind of like only gets the outermost corners. So if we had something like this, let's make something that's sheet metal. So we'll go sheet metal, base flange tab, create something like this. And then if we, oh, thanks a lot, John. Very much appreciate the value for value. That is awesome. Thank you, thank you, thank you. That's awesome. Thanks. So if we have something like this as sheet metal, if we use the regular fillet command and we pick this face, it tries to go around and get all of the edges of the, it tries to get everything. Obviously, that's not what we want. But if you use the sheet metal tool for, was it break corner? Yeah, break corner, corner trim. And then you pick this face, then it only gets these edges here. And it doesn't, it only gets the edges that would be appropriate for breaking those, break all sharp corners kind of a note. It also will kind of give you some interesting results if there's a pocket inside of that face. So if there's a pocket here inside of this face, and then we go to corners, break corners, corner trim, and we pick this. See, it's kind of interesting which ones it chooses to break and which ones it doesn't. So it really is interesting that it knows, break all sharp. It doesn't want anybody to cut their finger on those corners. So it breaks the correct corners, and you can do that using fillet as well. When you get in there, you go into corners here, you go break corners, corner trim, and then pick this guy here, and it only gets these ones. It doesn't get these ones here, which is pretty cool. Pretty cool that it knows. So just addressing that comment from Adam before we get back to work here. Very cool stuff. And thank you again so much to everybody for the support, whether that support is in the form of a like or a comment or, any way that you're able to support. I very much appreciate it. The value for value proposition is real, and there are a number of different ways you can support. Of course, the one way to support that I haven't mentioned yet is the softest t-shirts in the CAD game, the TooTallToby t-shirts. You can see that I've got one on. I've got one back there. I've got a few that I wear in rotation. They are absolutely the softest shirts in the CAD game. So if you are interested in getting a very soft shirt that you can wear almost every day, feel free to check it out. Or just buy 6 of them. Then you can just wear it every day and keep them in a nice rotation. It's always good to get a 6-pack of those t-shirts. Robert G says, soft indeed. We got confirmation co-signed from the chat. And Dritan R is in the chat. What's up? What's up, Dritan? Welcome, welcome, welcome. Of course, just a reminder for the remainder of the presentation, if you see something you like, put a 1 in the chat. If my audio sounds good, if everything sounds good relative to the music, put a 1 in the chat. Let me know that I've got everything leveled correctly, and we will proceed. A little bit of a history lesson here for those of you that are enjoying putting a 1 in the chat. I think you guys are going to enjoy this section a lot. A brief history of SolidWorks sheet metal. So this section, too, is all about sheet metal templates, and it's important to understand them. Francis Martin, thank you so much. Thank you, thank you, thank you. Very much appreciate the support. Means the world to me. Thank you, thank you, thank you. That is awesome. So understanding sheet metal templates, this is going to be a brief section, but I think it'll give you something to think about and hopefully help you avoid frustration down the road. And so what we've got here is the brief history of SolidWorks sheet metal. And what I mean by that, question came in here from Jitan R. It says, can I ask a question, but I need to upload a picture somehow here in the chat to explain it. The best thing to do there, Jitan, would be to go to the SolidWorks Discord. In the Discord, there's a forum for asking questions, and you can post a picture there really easily. That's the best way to ask a question. I can try to jump into there before I get off the live stream at the end and take a look. But that's going to be the best way if you have a question that requires a picture. So brief history of SolidWorks sheet metal. When it comes to SolidWorks sheet metal, I mentioned this earlier. Way back in 1995, SolidWorks was introduced to the world as a Windows desktop-based 3D CAD system for all engineers. And in 1997, they added sheet metal in the 97 Plus release. And that's when the insert bends functionality was added. We talked about insert bends at the beginning of this presentation. That's when it first came into effect in the world of SolidWorks. Then in the year 2000, SolidWorks came out with the release SolidWorks 2001, and the new sheet metal base flange and friends features were added. So base flange, edge flange, miter flange, hem, jog, all these cool sketch bend, all these cool new features were added in the 2001 release of SolidWorks. Then in 2013, there was another bit of functionality added, and that bit of functionality was what's known as the sheet metal multi-body functionality. So in 2013, we got tools that allowed us to do multiple bodies in one single part file for sheet metal. So you could have two sheet metal bodies, and then you could bridge them together, or you might have multiple thicknesses of sheet metal and want to design them all together. I mean, there's lots of reasons to use multi-body. But this is the reason why, whenever we're looking at sheet metal, we have a folder and a feature. So you'll notice over here, there's a folder that's called sheet metal. There's a folder that's called flat pattern. And then underneath that folder, there's a feature that's called sheet metal. And there's a feature that's called flat pattern. So there's a folder and a feature. And that's why we have both of them, because sometimes when you're working in sheet metal, you're doing multi-body design. And so you want to create your geometry in a way that those two bodies aren't necessarily merging. So you might create a second sheet metal feature over here that is not intended to be merged. So we go sheet metal base flange tab, and then maybe this uses a different wall thickness. So this one's going to use a wall thickness of 10 and a radius here of 15. And now we're going to bring that, down to a certain height. And those two need to work together in sheet metal. And so that's why we have this folder here to accommodate the multiple sheet metal bodies from this folder and the multiple flat patterns. It all needs to be organized. It needs to be understood by the software, so the software can generate drawings correctly of these different bodies and generate flat patterns and things like that. If I pick on this face of this model and then I click flatten, I just see a flat pattern of that body. If I go back to the main view, I see everything. If I click on this face of this body and click flatten, I just see a flat pattern of that body. And then if I go back to flatten, I see everything again. So that functionality, the software needs to know how to handle that functionality. And that's why there was new architecture implemented in 2013. What's up, Veluk? What's up, Veluk? From Finland. Welcome, welcome. Thanks for joining us today. So what? Right? Why am I telling you this? Why am I giving you this background of sheet metal? Well, again, in the spirit of trying to help you avoid frustration and trying to help you avoid errors, there is this idea of SolidWorks templates, and there's this idea of when features were created. So if I'm looking at this feature tree on the left, and there's a feature in the tree called starting tube, and I right mouse button on that feature and I go to feature properties, I can see on the right that there is a date created for that feature. So that feature was created on November 17th, 2011, starting tube. But what about your templates? When were your templates created? And what does that even mean, your templates are created? Well, not everybody knows this, but in SolidWorks, your templates are actually created by code that ships with the software. And what I mean by that is when you click new the very first time, you get a dialog box that says, do you want to work in millimeters or in inches? And after you answer that question, SolidWorks, the code in SolidWorks will generate new templates. And those templates will have a date of creation. And again, those templates are created from that code. Now, if you look over here, you can see that there were some templates that do ship with the software. These templates are from what's called the tutorial. They are the templates that you're encouraged to use when you're going through the SolidWorks tutorials. And if I right mouse button on the front or the top or the right plane here, and I go to feature properties, I can see that this template was created by D. Levine back in 1999. That's an old template. Back in 1999 is when that template was created. So when the person who created this template, what they did was they launched SolidWorks back in 1999. They said new for the very first time, and the 3 new templates were created, part assembly drawing, using the architecture and the code that shipped with that version of the software. So in this case, what's on my screen here, you can see that I did a right mouse button on the front plane, went to properties, and this one was created by Fred, by F. Kolar, back in 2000, March 27th, 2000. Hey, almost exactly 23 years ago. That's pretty crazy. So this was created back in 2000. Now, why does that matter? Well, like I said, there were new tools implemented in 2001. This is a screen capture from the What's New. And there were new tools implemented in 2013. And as somebody who worked in tech support for many, many, many years, we would get a lot of questions like, why do some sheet metal parts not have the cut list flattened mass properties? The answer is the flattened mass property is part of the sheet metal architecture that was implemented in the SolidWorks 2013 software. When you have a template with sheet metal features, even after deleting features, internally the template still contains the sheet metal information. If you created these templates prior to the release of the 2013 software, the sheet metal information will use the previous architectural code. If the flattened mass property is important to you, then you should recreate the part template you use for your sheet metal parts. That's one example of a tech support case, a knowledge base article that has to do with this topic. Here's another example. Bend lines are no longer showing in a drawing after updating from SolidWorks 2012 to SolidWorks 2014. How do I get bend lines to show again? And I'll skip this to the important part. It is strongly recommended that the customer installs the latest version of the SolidWorks templates in order to proactively avoid this issue. So the lesson here is that if you're working with templates that come from before these key dates, if your sheet metal isn't working correctly, you want to make sure that you make new templates. I mean, really, if you're working with older templates, you probably want to just proactively make these new templates. So what you do is you go into your system options and you look at all these different paths here. So in my system options, I think there's 4 of these paths. File locations. You're looking for the library of your document templates. So the library of my document templates here is pointing to these 4 different locations. Well, these locations are going to coincide with the new command. When I click new, you can see that I've got these same 4 locations here. So the same directories that I'm pointing to in my system options show up here. What you want to do is you want to go into that directory and clear go into that option in your system option under file locations. You want to clear all of these until you just have the one, the main, the default directory. So you're going to go in there, you're going to see that that's the default directory, the install directory. You see program data SolidWorks, that's what it starts with. And you're going to clear those templates out of there so that that folder is empty. You're going to make sure that in your system options, you're only pointing to that one location, and then that location is empty. And then you're going to click new, file new in SolidWorks. This is me looking at my Windows directory. That folder is empty. I go file new. I say I want to be working in millimeters and ANSI. I click OK. And then that directory gets populated with the part assembly and drawing templates. And then if I look at the date created on one of those, I can see that the date created is today. In this case, it was from last year, 3/20/2022. But the point is that I'm looking for templates that are created after 2013 to make sure that they have the correct architecture. If you don't do this, you might run into some kind of like weird functionality in sheet metal that just doesn't work right. The key dates here are 2001, 2013. The base flange and friends were added in 2001. The multi-body support was added in 2013. And if the date created is before 2013, it's probably worth it to go through that exercise and create some new templates. You can't just do a save as, like open the template, do save as, and save it as a new template. It has to be created anew. And that's the end of that section. A very short section, but just a brief history of sheet metal, just to help you understand that templates are a common cause of problems, because a lot of times a company will create a template and that template will be in the software in the company for years and years and years and years and years. And it might even be from before 2001. It's going to create the template with the architecture of the SolidWorks version you're running. Yes, that is correct. That is correct. It's pulling the code from the version that you're running when you do file new, and then it's using that to create the new version. I mean, it might be older code that they reused over and over again. It's not, the code doesn't necessarily update every year, but yes is the short answer to your question, Ivan. It's going to use the code from the version that you're currently running. And that is a little brief history of templates in SolidWorks and why they are important to sheet metal. And that brings us to our last section here, flat patterns explained and dissected. And so when it comes to flat patterns in SolidWorks, there are some key things that you want to look out for with flat patterns. I mean, the first thing we've already talked about a lot is the idea that when you go into a flat pattern, there's deformation taking place in the corners of your sheet metal. But there's some other important information to recognize, like what does this icon actually do in the SolidWorks sheet metal tab, in the command manager tab? What does the flatten icon actually do? Well, what the flatten icon actually does in reality is I'm going to just close everything here. I don't think I need any of this stuff right now. What the flat pattern does is it suppresses and unsuppresses the to open this part, the feature that is found in this folder. So there's a feature here called flat pattern 3, and what that feature does is it takes all of these formed bends and it unfolds each of those formed bends. So we've got this this bend here, and we've got this bend here, and we've got this bend here and here, all these bends that are on here, and it takes all those bends and it unfolds them. I actually expected there to be more bends, but I guess it just kind of collected them all. Okay, there we go. Now it's got all of them. This just needed a refresh. So it's just taking all of those bends and it's unflattening them or unforming them. And so you can see here that when I click that button, it's just taking this feature and it's unsuppressing it. In fact, if I unsuppress this feature, that button gets pressed down. If I press this button, the feature gets suppressed. It's the same thing. It's just a shortcut. That's all it's doing, and it's not doing anything else. And that's very important to understand because there's this idea of what I like to call the sheet metal sandwich, which is that every feature that you create should always exist between these two features here. You should never have a feature that's created down here below the flat pattern feature in the tree. And so if I go to flatten and then I create a cut extrude here, like so, extrude cut, and then I unflatten this, so I click the button. So I had to unsuppress this feature in order to get that flat geometry, and then I created the cut extrude. Well, now that cut extrude is in a bad spot. It's outside of the sheet metal sandwich. It's out here. Ugh. That's not what we want. That's not a good sandwich. And so when I go back to flatten, look, that feature is not shown anymore. That is not good. So I actually just made a video on this recently, this idea of the flatten the sheet metal sandwich. But the idea is that you click this face, you go to unfold, which is a feature up here on your sheet metal toolbar, and then you can unfold this bend. And now that unfold is inside of the sheet metal sandwich, and then you can create a cut extrude across that bend. So extrude cut, and then you can fold and turn that back into a form shape with that cut going across the bend. And the reason this works is because everything is in between these two features. So first and foremost, clicking this button up here doesn't do anything more than unsuppressing this feature. And it also sets you up so that any new features you create are going to be created after that feature in the tree. And you really don't want that. In sheet metal, you want to have that sheet metal sandwich. I just made a video on this on the TooTallToby channel. The unfold and fold video, or I like to call it the SolidWorks sheet metal sandwich. Very good video to watch to understand how that fold and unfold works. So then the question is, how do you make a flat pattern configuration for a sheet metal part? And this is an important question because what a configuration is, just in case anybody's a little bit newer to the software, the idea of a configuration is that you can create parameters that can be either changed numerically or can be turned on and off in different versions of the same part. So for example, I've got a fillet here on the top of this part. I could make a configuration here, add configuration called no fillet, and I could take that fillet and turn it off in this configuration only. So I've got a default where the fillet is shown, and I've got a no fillet. And if we split this tree here so you can see both, you can see that fillet becomes suppressed or turned off in one configuration and becomes unsuppressed in the other configuration, or turned on in the other configuration, suppressed, unsuppressed. So the ability to turn features on and off is part of the idea of configurations, and also the ability to create things that are different numerical values. So I could take this 25 here and make it 75 and say that's only for this configuration. So now I've got a tall configuration, a default configuration, and a no fillet configuration. And maybe in the tall configuration, I want the fillet to be unsuppressed. So I've got a no fillet and I've got a tall with a fillet. This is the idea of configurations in SolidWorks, a very powerful tool. Not just tall, but too tall. Yes, that's correct, Adam. A very powerful tool in SolidWorks in general. And we could certainly do this with a sheet metal part. We could make a configuration here, say add configuration and call it flat. And then in this flat configuration, we could take that flat pattern feature and unsuppress it. And there we go. Now we've got a default configuration and a flat configuration. Oh, awesome. We did it, right? No, that is not the way you want to do this. This is not the way to create a flat pattern configuration. The way that you create a flat pattern configuration is you make a drawing. And the reason why you do it this way is because it's not just a regular configuration, it's actually a derived configuration, and it's got a special naming convention as well. And you'll get different behavior if you don't do it this way in the drawing. So what I mean is, here in SolidWorks, I'm going to go to the command File, Make Drawing from Part. Now, if you look at the tree here, you'll notice that there's only this one single configuration. There's no other configurations in this tree. File, Make Drawing from Part, and we're going to just use the Model Monday Live template. And at this point, I can see that this part is in both the formed state and the flattened state. Now, the only way that we can show a part simultaneously in two different states is if we have two different configurations. It's how you do it in drawings. It's how you do it in assemblies. If you don't have two different configurations, you can't show the part in two different states simultaneously. And so without even dropping in a drawing view here, I'm going to cancel this command. I'm going to look at my tree over here, and I'm going to see that a new configuration was automatically created. And it's a derived configuration, and it has the correct naming convention. And so this is really an important lesson in the world of sheet metal. If you want to create a flat pattern configuration, the way that you do it is you go File, Make Drawing from Part. And then after you create that flat pattern configuration, just leave it alone. Most of the time when people get in trouble with sheet metal, they get in trouble because they try to manipulate the flat pattern configuration. You know, especially if you're just getting started in sheet metal, once you create that flat pattern, just leave it alone. Don't touch it. Don't go into that mode. Just completely leave it alone, and you'll probably avoid a lot of the most common problems that people run into with sheet metal. So again, the workflow, I've got one single configuration here, default, File, Make Drawing from Part. I'll do the Model Monday Live template. And just by creating a drawing, I don't even have to drop the flat pattern on here if I don't want to. Just by creating the drawing, that automatically created a new configuration here for the derived flat pattern configuration. Now, if I do drop that drawing view on here, what'll happen is I'll get some special functionality from that drawing view. So when I look at the drawing view properties, I've got things over here like flat pattern display, bend notes, and I've also got the ability to flip the drawing view. So if I was worried about these edges having a burr on them because of how the punch goes through, and I want the punch to go through the other way, I can pick up that entire drawing view and flip it over. So it's not just a rotate, it's actually flipping it. It's changing the direction of the bends here. You can see the bends are bending up, and then when I flip it, now the bends are bending down. So it's actually flipping it over so that when you manufacture it, you can get the burrs going in the desired direction. Now, I'm pointing that out to you because if I close this drawing and then I get rid of this extra configuration and then I make my own new configuration, I'll call this flat pattern. So now this is a new top level. It's not derived. And then I go to the flat pattern feature and I unsuppress it. Okay, so now I've just got this default and I've got this new configuration that I created. And then at that point, if I go to the command File, Make Drawing from Part, so I'll make this this drawing using the same template here. And then let's just say I drop in a top view of this thing, and I go to the top view, and I change the configuration here to flat pattern. Well, you'll notice here that in flat pattern, I don't have that extra functionality. So that bend notes option and the flip view where you pick it up and you flip it over on the sheet, those didn't show up for me in this configuration. So just an example of why it's important to follow this workflow. Use the command File, Make Drawing from Part. This is how you make a flat pattern configuration. And when you use the command File, Make Drawing from Part, you're going to start out with one single configuration, and then as soon as you make the drawing, you're going to have that flat pattern configuration. And after you make that, just kind of like leave it alone. So after you use that File, Make Drawing from Part, it'll be a derived configuration. Don't try to make one on your own, and just leave it alone. The other detriment of making your own, especially if you make it top level, is that it is not derived. Now, what derived means is that the dimensional relationship, it means you can create a dimensional dependency to the parent configuration. And so what I mean by that is if I look at say this side edge here, and that side edge is coming from this sketch, and this sketch has a dimension in it of 50. Well, the relationship here is set normally to link to parent configuration, And so what that means is if this 50 dimension changes in the formed view, it's going to automatically change in the flat view. Well, that's not going to be the case for the relationship between default and the flat pattern that I created. So let me delete that extra one. So we've got this default and the flat pattern I created. Well, let's go back to default now, and let's change this dimension here from 50 to, let's say we change it to 25 for this configuration only. So we rebuild, and now this is what our model looks like in the formed state. Well, when I go into the flat pattern, it didn't pick up on that change. So I'm still going to be cutting these parts at 50, and the customer wanted that height to be decreased to 25, and so I'm going to be, making bad parts here. So you have to be aware of that. You have to be aware that, the best way to make a flat pattern configuration is don't make it on your own. Just make it by going to the command File, Make Drawing from Part. That's the way that you do it. And that will keep you out of a lot of trouble. And you'll get that special functionality, and the flat pattern will always be synced to the formed one. So when you change the form, it'll change the flat. All righty, cool. Thank you, Richard. Appreciate it. Thank you, Sally. Appreciate it. I don't think you have to cut out early, Richard. I think I'm running long here, but that's okay. You can watch the recording if it's if you want to come back to it a little later and watch it. So just a couple of final options here to review with you guys with regards to the flat pattern. There's mainly two options you want to be aware of. The fixed face option. So you go into the flat pattern, you say Edit Feature, and you've got the option for the fixed face, and the Merge Faces option. So you go in, you can merge those faces. And finally, the corner treatment option. This is a really important one. Some of the other options are a little more nuanced, and I'll kind of touch on them just a little bit, but I think these are probably the most important ones. So whenever you're looking at a sheet metal design, let me change this back to 50 so that miter looks just a little bit better. Oh, I'm looking at this in perspective. That's why I'm struggling so hard to hit those dimensions, because I've got this thing in perspective. Okay, so we'll rebuild that and go up to 50. Okay, cool. I'm going to delete that flat pattern config. And so now what I'm going to do is I'm going to go over here to my sheet metal flat pattern feature, and we can right mouse button on this feature and we can choose Edit Feature. Now, when we choose Edit Feature, we can see here that there's an option for fixed face. And most of the time you don't have to touch this feature. But what this feature does is it lets you pick a face off of your model that remains stationary when you jump into a flattened view. And so like I said, most of the time SolidWorks does a good job of selecting it, but there are times when things get a little bit funky. Like if I make a part that looks like, let's say I make a part that looks like this. Come over, come up, come over, and then bring a line down here and make this for construction. And then I'm going to mirror this geometry across. And now I'm going to turn that into a sheet metal part using base flange tab. So we're going to take this, we're going to turn it into sheet metal. We'll say that we're at 4 millimeters with a 5 millimeter bend radius. Now I'm going to go to flatten, and what's that? What's that all about? Right? Why did it end up at this? That is not what I wanted that to do when it jumps into a flattened view. That's just like awkward. Well, this would be a good time to know that you can right mouse button on the flat pattern feature in the tree, go to Edit Feature. You can examine which face SolidWorks selected. So they selected this angled face here on the inside, and then you could change that to the desired face, this face up top here. Hit the green check mark, and now I go into the flattened view, and boom, that's what we wanted. So the ability to edit the sheet metal flat pattern feature and choose the fixed face, not one that comes up too often, but when your sheet metal is not unflattening in the desired orientation, like if it's unflattening at a funky angle like this, then it's good to know how to get in there and quickly change that in the flat pattern feature. So fixed face, that's the first feature that we're talking about in the edit flat pattern. The next one here is the merge faces command. So what the merge face command does is it lets you take your sheet metal flat pattern and merge it all together into one face, or show the individual faces where the bends are. And this comes in really handy when you're trying to export something to DXF, DWG. So if we go to the edit feature here, I'm going to change that flat face back to this one, or the fixed face back to this one. And we go to flatten. Now we want to do a right mouse button and we want to do a save as DXF, DWG, or export to DXF, DWG. Well, we don't want all these individual faces and all these extra lines. That's just going to, require me to clean that up before I send it out to the water jet. So we're going to right mouse button here on the flat pattern feature, say edit feature, and say merge faces. And then we hit the green check mark, and now this is all one face. So now when I do a right mouse button and I say export to DXF DWG, now it's all just going to be one single face that goes out to that DXF DWG. So that's the merge faces option that's in your flat pattern options. You go into edit feature on the flat pattern. If you want them to be individual faces, this is really useful when you're examining, like, is it unbending correctly? When you're troubleshooting K-factor, bend deduction, bend allowance, very helpful. But when you're trying to export to a DWG, then, Can you right click when the model is unflattened? Yes, you absolutely can. You can export individual faces for a variety of applications, export to DXF, DWG. When it is a sheet metal part, I think you get an additional property manager after you save it. So we'll call this one export to DXF and save. And then see, it gives you these options over here. But even if it wasn't a sheet metal, you could just take one face and kick it off. If you were like trying to mask a decal onto it, and you needed a one-to-one of that face so that you could then, put it into like an Adobe program, a photo editing program to size up a decal. Very, very useful application. There's a lot of different applications of this, but yep, it doesn't have to be formed. It doesn't even have to be sheet metal. You can right mouse button. You can export a face to a DXF. Great question from Daniel there. Let's see here. See if you can draw an oil filter can in sheet metal. Yeah, I mean, the oil filter can example, we actually talked about that a little earlier in the presentation. You could just do it as a cylinder, extrude it, and then like add a fill pattern to it. So there's a couple ways you could do that. I'm going to just get slightly derailed here just because this won't take too long. So if we make this what you really want to do is you want to split this. I mentioned this before. You want to create some kind of a split here. A lot of times, I mean, there's several different ways you can do this, but a lot of times I just make it like a little Pac-Man there. And then you could either extrude that as a thin, or you could even extrude it as sheet metal right from the jump. So you could create an extrude like this. And then what you could do is unfold, and you pick this edge here to unfold. So that gives you this geometry in the flat there. And then you would do a fill pattern. So you go features and make this a fill pattern. And you could say that the seed is a hole. And that's going to be on this face, and this will be in this direction. There we go. And then we could say that we want the spacing between those instances to be a little bit more, like we'll make that 25, and then we'll make the diameter of this, say 15. And then we hit the green check mark, and then you can go back to your sheet metal tools, and you can do fold and collect all bends. So anytime you need something like that, that's going to be, cylindrical, that's how you can do it. You can unfold it and then refold it. I mean, obviously, I would put a lot more attention to detail into this, but that's the idea. Yeah, cone, same thing. You can do the cone the same way with a cone. So, yep, you can definitely do it if you learn how to use some of these different sheet metal tools and fold and unfold and tricks like that. All still kind of in that same realm of flat pattern, right? The flat pattern options are very important to understand. Another flat pattern option that's really important to understand is this option for what's called corner treatment. Now, this is a little bit of an old school mentality when it comes to this corner treatment idea. But the idea is that after you turn your model into a flat, you go around and you relieve these regions where the bends are taking place. So the bend you can see here is all coming together at this one spot, and that's going to be very difficult to bend. And so from corners here, you can choose what's called corner trim. And then for corner trim, you could say that you want there to be an 8mm diameter punch that you're going to punch through there on the corner. And that way, when you export this thing to a flat and you send it out to the shop, they've got plenty of relief there to bend those corners and, hopefully not have them be problematic with too much wrinkling or anything. The problem with this mentality is that what you see in the flat really does not match what you see in the formed. Like this coming together at a sharp, that is not how I expect that to look in the flat. I expect it to be the 1, 2, 3 faces here coming together at 90-degree angles. And the reason that that happens is because in the flat pattern feature, the edit feature of the flat pattern, this option here is checked on, corner treatment. So a better way to do this, if that's what you need, a better way to do this is first to uncheck that option. First of all, that'll give you the actual correct geometry in the flat. So you see here, that's what it looks like in the flat. And then if you do need that kind of corner treatment, you can either use this tool here. There's a corner relief tool that you can use that's specifically for that purpose. Or you can use the unfold fold technique that I showed you earlier, where you could unfold this and then you could create those punches in the corner. Let's say I make these 10mm diameter and, and locate it appropriately. And then I'll control drag this over to here to make a second one. And then we do an extrude cut. And once we do that extrude cut, we see that's what those features look like. And then when we go to fold and we do collect all bends, now we've got ourselves our formed shape again. And so now what we're seeing in the form matches what we see in the flat. So I like that a lot better, but it's a really common question that we would get in tech support is, what is the idea? Like, why is this sharp here? This shouldn't be sharp. If we're looking at it here in this corner, it should not come to a sharp like what we're seeing there. And that's the answer to that question is the corner treatment option. So there's a lot of options that are in here in sheet metal. One trick that I often teach my students about is if you go to any feature in sheet metal, you can launch the help for that feature. Now, what I personally do is I go in here to the help question mark or the help pull down menu in the older versions, and I uncheck the option for use web help because it's a lot faster to search help when you're working locally. But once you uncheck that, then you could go into any feature. Like I could go in here and I could say edit feature on the flat pattern, and I could click on the little question mark here for help. And then this shows me the help specifically on that feature. So it's the help regarding the flat pattern property manager. And so then from here, I could say like, well, what does simplify bends do? Oh, okay, I can see here when there's a bend region, that's what this region is here, it's a bend region, and there's curved geometry running up to that bend region, it takes that curved geometry and changes it to just be a straight line. Okay, that's kind of cool. What's this show slit? What's that do? Oh, well, when there's a corner relief that's, that's cut as a rectangle, it'll show you an additional slit there that needs to be cut to almost like to relieve the relief. It's a weird kind of, I guess you'd call that a corner case, right? A fringe case or a corner case. What about grain direction? What's grain direction do? This option over here for grain direction. Well, if you've got multiple components that are coming together, aesthetically, you might want to have the grain all running the same direction. Sometimes structurally, it's important to have the grain running the same direction. So you can get an annotation on your drawing, a little arrow that shows the grain direction. And how about this last option down here, faces to exclude? Well, faces to exclude would be if you were working with formed features and you didn't want to show them in the flat pattern, you could use that faces to exclude option. So that's the end of our sections here, sections 1, 2, and 3. And I think this is pretty good stuff. Alday is saying, for large sheet metal parts, I lay the flat pattern inside a rectangle to represent the raw sheet material 4x8 to make sure the fab shop can make it. Yeah, that's good. That's very good advice. Make sure that you know what kind of table, what kind of max envelope your shop has for cutting. Barry is reminding us that there is a CSWP for sheet metal. That's good to know. Good to know. If you guys have any questions for me, please let me know those questions. I'm going to do a little, I think I'm going to do a little bonus round here for you, a little fast money round as we wind down this presentation. During this fast money round, if you have any questions, let me know. Don't forget, it's a great opportunity to like, to share, to subscribe, to comment, and of course, to send some value for value during this fast money round. But I'm just going to do a couple of quick things here that I think are valuable lessons that I learned from sheet metal that I can use in other places in the software. And the first of those valuable lessons is the idea of the soft relationship. So again, during this fast money, during this bonus round, if you guys have any questions, please feel free to type them in the chat. But I'm just going to run through a couple of quick things that I've learned about SolidWorks from working with sheet metal. So the convert entities yields a soft relationship. And what I mean by that is whenever you create an edge flange in SolidWorks, like if I go here and I say I want to make an edge flange, that edge flange has a sketch which has black lines, black line here and a black line here. So that would mean that those are fully constrained, right? But you can grab that black line and you can drag it and it becomes a blue line after you drag it. Huh, that's kind of interesting. That's something that I learned when I was working in sheet metal, but I learned that it applies to all areas of SolidWorks and it yields what I like to call a soft relationship. And what I mean by that is anytime we create solid geometry and then we create additional geometry on that solid geometry, we could pick this back edge of the part here and do a convert entities. And then we could choose to sketch additional geometry. So I'm going to sketch a line here that goes vertical and a line that goes horizontal and then a final line that goes vertical here. And you can see that those lines are black. This line is black and this line is black. And that means it's fully constrained. And that means that if I edit the original sketch and I drag this line over here, that relationship is maintained. This line that I sketched moved with that edge as I moved the base geometry. But if I edit this sketch and I grab this black line and I move it a little bit, I just broke that relationship. And now if I go back to the original and I change that sketch and move it over here, now we see that the new sketch did not move. And that is what I like to call a soft relationship. It's something that I learned about in sheet metal by manipulating the sketches of the edge flanges, but it works everywhere in SolidWorks. And there's been plenty of times where that has been handy because sometimes what you'll do is something like this, where you will take this edge here and you'll do a convert entities and you don't have to trim that edge. You just grab this endpoint and you drag it down and then you can start sketching from there. So very cool stuff to know about in the world of SolidWorks, which I learned from the world of sheet metal. The black line can be dragged. Another thing that I learned about from sheet metal that I use a lot in other areas of SolidWorks is that when you're creating a miter flange, you pick this edge and a new sketch plane is automatically created. Well, that works all throughout SolidWorks as well. So if I was to create some kind of a cut extrude here, and then I was to pick this edge and choose to begin a new sketch. So I just pick that curved edge and begin a new sketch. Look at that, SolidWorks automatically created a new plane perpendicular to that edge at that point. And if you do a lot of sweeping or lofting, that's very handy to know about, that you can automatically create a new sketch plane just by picking an edge and choosing the sketch command. A new sketch plane is created perpendicular to that edge at the end point. This is something that I learned about by using sheet metal and doing the miter flange command, but it works all throughout SolidWorks. And another topic that I learned a lot about by working in sheet metal is the idea of display states. Display states are, they can be very confusing if you don't really know how they work. But generally speaking, display states can be linked to configurations, and in sheet metal, you do not want this. Generally speaking, you really don't want this. That's kind of like the lesson that you learn. But a lot of times in sheet metal, you make the flat pattern configuration, and the display states end up being linked. And the idea of a linked display state is basically that when you're working in SolidWorks and you create configurations, you can have those configurations automatically linked to display states for things like color changes. So if I create this part here and I call this one short, and then I create a new configuration, so I'll say add configuration here, and I'll call this one very short. And then I'll create one more configuration here, and I'll call this one big. Now I can change this dimension here for this configuration only. And I can say that I want that dimension to be 8 and rebuild. And then for very short, I can change this dimension, and I can say that I want that dimension to be 2 and rebuild. So I've got big, short, and very short. Down here in the display states, there's one single display state. It's called display state 1. If I right mouse button on that display state and I say properties, I can say that I want to link my display states to my configurations. And what this does is it allows you to change the color of your model for this display state only. This display state only. And so when I hit the green check mark, I could have a green version, and then I could change the color again for this display state only and have a purple version. And then I could change the configuration again and have it change again. And so what's happening here, if you watch down here under display states, the display state changes as I change my configurations. You really don't want that in sheet metal, and it can be pretty annoying when you make a flat pattern and the main configuration is like shiny metal, but then the flat pattern is like a dull gray because it uses the default color. So this is just like another lesson that I learned from sheet metal. I really learned how display states work in general, but if you don't want to go through and learn how they work, just understand that you can right mouse button here and you can say linked display state or not linked. You really don't want them linked. You just want one display state to work across all your configurations. So that's something else that I learned from sheet metal. And then the final topic in this bonus round is that when it comes to multi-body design, you can use that all throughout SolidWorks. It's not just in sheet metal. You can use it in weldments. You can use it in regular multi-body part design. You can do this thing where you do model view, and then you do select bodies, and you can add those different bodies to your drawings. So the ability to do multi-body drawings is something else that I learned from sheet metal. So there's your notes for bonus round, and I think that's going to bring us to the end here. I'm out of my special emergency vitamin C drink, so that's a good time for us to kind of start to wind this down. Let me take a look at the questions that came in here. We had some really good questions come in, so let me flip over to back over to my SolidWorks view, and we'll take a look at some of those questions that came in. Alrighty, let's see here. What do we got in our questions? Sheet metal features work for product box design from cardstock. Sheet metal features work for product box design from cardstock. Yes. Yeah. Oh, yeah. You can use it for cardboard. I think that's what you're saying, right? Yes, you can definitely use it for cardboard. The bend deduction calculations get a little bit dicey, but you can absolutely use it. Nuno says tab and slot. Any tips? I've used tab and slot a lot. I can tell you some stuff on it. It does work well. It usually works, for me at least, it usually works best when you do it with multi-body rather than trying to do the tab in one part and the slot in another part and then do it as an assembly in context feature. So try to do it as a tab and slot. That'll definitely, in a multi-body part, that'll definitely work better. Ivan confirms tab and slot is great, but it's got a lot of bugs. Be prepared. Yeah. Forming tools would be great to learn some tips there. Okay, this is good. I think I'm going to do an advanced sheet metal tips and tricks live stream. So I think this sets the foundation nicely for an advanced tips and tricks, and these are great suggestions for that. Adam says +1 on soft relationship. Yeah, definitely good to know about. And convert to sheet metal, we covered that in the beginning of the presentation. So if you just roll back about an hour in the presentation, you'll see all the convert to sheet metal stuff. There's some really good stuff there. Display state, the least known and used feature. Yeah, I need to make a video on display states for sure, because once it's explained, it makes sense. But if you don't really know what's going on, it's terribly frustrating when the part just changes color and you're like, why did that change? All I did was go from a form to a flat view, and now I'm changing colors. That's the most annoying one, is when it takes the default color for the flat pattern when you make your flat pattern configuration, and these are linked. So let's see if I can get it to happen here. So I'll go properties, link, hit the green check mark, and then file, make drawing from part, and we'll make a new drawing here. And then we will just cancel that drawing because we don't actually need a drawing here. We just wanted to make the configuration. And now we've got this new configuration here, and we look at this new configuration. See, it's a slightly... I think it's a slightly different shade of gray. Oh, no, those look like they're the same. But that's the most common thing that I see, is that it ends up in this display state being a slightly different shade of gray. It takes the default color, really. So it just takes this default color here. So then you're like, wait, this looks good in this view. It looks like the nice sheet metal, nice sheet metal finish there. And then in this view, it just looks like a dull gray. And, you're not sure why. And the reason why is because of display states. That's the reason why, ultimately. So, yeah, see, it's just slightly different. It's just enough to be annoying. And that's why. It's because it's a linked display state here, and it's changing between the two display states, which is changing the color between them. So you right mouse button here, you go to properties, and you say, don't link. I don't want the link anymore. And then you delete the extra one. Delete the extra one from the tray. All white is hard to view. Okay, yeah. I'll keep that in mind for future videos. Thanks, Niku. Appreciate the feedback on that one. That's good to know. All right, so that brings us to the end, and I guess that brings us to our goals, review of the goals here. Let's see if we accomplished our goals for today. So do you understand the different ways to approach sheet metal, the different circumstances that determine which technique to use? There's going to be a quiz here in a second, so you guys be ready to answer. If you don't answer these questions, if you don't know these, then I didn't do my job. Do you know the best way to make a flat pattern configuration? Do we all know the best way now? Do you know the key options found in the flat pattern feature and how to adjust those key options? And finally, did you learn at least one additional tip and trick? If you did, well, here's your chance to prove it. So first review question for everybody in the chat. How many common ways are there to begin a sheet metal model? How many common ways? How many common ways are there to begin a sheet metal model? I'm going to take a sip of my coffee and wait for you guys to answer this question. How many common ways are there to begin a sheet metal model? Let's see what we got here. Let's see what people think about this. Were people paying attention? Did we accomplish the goals? That's what we're going to be finding out here in just a second. And it looks like the answers are coming in, and it looks like the answer is 3. 3 is the correct answer. The correct answer is 3. Good guess, Zoltan, 1001. 3 is the correct answer. There's 3 common ways. There's the insert bends technique, there's the base flange and friends technique, and there is the convert to sheet metal technique. Now, there are other ways to do it. You could do lofted bends, you could do a swept flange, you could even do a surface flatten, which we will talk about in the future. Surface flatten is a very powerful command when you can't get your sheet metal parts to flatten. A lot of times you can get them to with surface flatten, but yes, that is correct, 3. All right, next review question. 1-1 binary, very nice, Robert. Which method would you use for, okay, here's the question. I'm gonna kind of cruise through these. But I do want you guys to answer them in the chat. But as we're approaching the 12:30 time here, I want to just kind of wind things down. But I still want you to answer these in the chat. Which of those 3 techniques would you use for a new design? So the 3 techniques are insert bends, base flange and friends, or just base flange, or convert to sheet metal, or you just type convert. So for a new design, something that looks like this that we see on the screen here, which of those techniques would you use? The insert bends, base flange, or convert to sheet metal? Which would you use? So for a new design, which would you use? All right, what about this one? What if you got an IGES from the customer, and after you get that IGES from the customer, you do a thickness analysis, and you determine that the entire model is uniform wall thickness? Would you use the base flange command? Would you use the insert bends command? Or would you use the convert to sheet metal command? Which one would you use for the second one? You get an IGES from a customer, and you need to turn that into a sheet metal part. And then finally, this third challenge here, for this third challenge, what if you had a 2-piece assembly with complex angles? Which technique would you use? Would you use the insert bends technique? Would you use the base flange technique? Or would you use the convert to sheet metal technique? Because the goal of our training today was to teach you, that there are these 3 different techniques, and there's going to be different circumstances where one might be better than the other. Sure, they could all be used kind of interchangeably, but there's going to be some spots where it's going to be, very clear which technique you want to use. All right, and I'm seeing the answers coming in, and I think that you guys all got these correct. This first one, this would be using the base flange and friends command. You'd create your initial flange, and then you'd be able to go around and add your edge flanges. This looks like it would almost entirely be edge flanges for this one. Maybe one miter flange in there for that weird bendy thing, but almost entirely edge flanges. Very nice. This one here, the uniform wall thickness, IGES from a customer, insert bends, or maybe convert to sheet metal, depending on which one. But I think insert bends would probably be a little bit easier, because convert to sheet metal, you'd have to go around and pick all the edges, and but you could go either way. I mean, convert to sheet metal has the advantage of auto ripping, so kind of pros and cons to each. And then this one here, the complex with bend angles, this would definitely be convert to sheet metal. All right, awesome job, everybody. 2 more questions for you. This one here, how do you create a flat pattern configuration? How do you create a flat pattern configuration? Right, this is a very important question that anybody who's getting started in sheet metal should know. Maybe you're even a seasoned pro, right? Maybe you have been using sheet metal for a long time. How do you create a flat pattern configuration? All right, excellent. Seeing all this great feedback. Drawing, create a drawing from part, and Zoltan says fully define. Yes, that is the correct answer. Very nicely done. That is correct. You're going to be using the command file make drawing from part. That is excellent. Great job, everybody, on that one. And the final question here. My flat pattern doesn't look right. What should I do? My flat pattern doesn't look right. What should I do? So my flat pattern, the model looks good in the formed view, but my flat pattern doesn't look right. What should I do here? And this is just one of these questions. I wanted to include this in the review because this is something that a lot of people run into this. A lot of people have this problem where, you know, they took their time and they got the formed model to look great, but then the flat pattern doesn't look right. Check your corner treatment. Exactly, Nuno, you got it. You got it. Go to the flat pattern feature, adjust the check mark. Yep, you got it. Exactly. There's that one flat pattern option. There's really two in here that get most people. And that's merge faces and corner treatment. But that corner treatment option is saying that you plan on doing some manual corner treatment, you know, later on. If you don't plan on doing that, then you really don't want that option to be checked on, or else you're not going to get the correct geometry in the flat. So very nicely done to everybody. You guys crushed it here. That brings us to the end. Let me know if you guys have any other Q&A. I'm happy to draw up anything for you guys and answer any questions you have, but that does bring us to the end. Be sure to like, be sure to subscribe, be sure to comment, be sure to share. It is super helpful to keep this channel going. Any value for value you want to send my way is always very much appreciated. Don't forget to buy the softest t-shirts in the CAD game. These are amazing black t-shirts that you can wear every day to every event. Huge thank you to our sponsor today, SolidBOX. Go to mysolidbox.com the next time you need to get a new computer. They will absolutely take care of you. And that's going to bring us to the end of Sheet Metal. I want to say thank you to all of you, the most amazing chat ever. You guys are great. I really appreciate all your feedback, all your interactions. All the ones in the chat were great. If you had a good time today, be sure to put a 1 in the chat before you go. Victor K is here. Thank you, Victor, for joining us. Very much appreciate you being here. So good to have you in here today. Victor K is here. Everybody say hi to Victor in the chat. Put a 1 in the chat for Victor. Thanks, Sally. Thanks very much. That is the end of our digital 3D CAD users group. Will we do another one on April 25th? I don't know, maybe. Let me know in the comments if you want to see more. After this thing gets posted, you can go into the comments and you can say, yeah, we should do one on surfacing or tips for sweeps or advanced sheet metal or weldments or, you know, whatever it is that you guys want. I can see if I can make it happen on April 25th. That's going to be the last Tuesday of the month. I thought when I read your comment there, Victor, I thought you were saying, gotta go. Gotta go. Sorry, Tobe. See you later. All right. Ashok, thank you so much for joining us. Nuno, thank you for joining us. This was awesome seeing everybody, catching up with everybody again. Let's see. Sally, thank you so much. Robert G, thank you. Thank you. Rich K, wearing my shirt now. Softest in the closet. Yes, I appreciate it. Appreciate it. And Alday, thank you very much for the awesome interactions in chat today. Victor says, gotta go beat Airwick's time. Yep. Don't forget, guys, we got the 3D CAD leaderboard at TooTallToby.com/leaderboard for people to challenge themselves. I'm going to try and do it this week in Onshape. I'm going to try and run that thing in Onshape this week before March expires. So I'll be hot on your heels or on Airwick's heels. Adam, thank you so much for joining us. Great seeing you in here today. Thanks for all the chat. Niku says, you deserve more viewers. Oh, thank you. Thank you very much. Appreciate that. We'll get there. Don't worry. It's a slow and steady progress, and it's, you know, the content in the space of edutainment is not nearly as popular as, like, you know, going out and pranking people or whatever, but that's not really what I'm into. I'm actually trying to use the internet to spread educational value. So it's a novel concept, I know, but it's okay. It'll catch on eventually. Eventually people will be like, oh yeah, this is what we actually needed it for. Johnny says, thanks. Thank you, Johnny. Appreciate it. Appreciate it. And Ganga Tech says, thank you. Thank you very much, Ganga. Appreciate it. Appreciate it. And you guys have a great rest of your day, your Tuesday. Have a great rest of the week. We're winding down the month. Don't forget, if you're looking for some fun times, you can check out the TooTallToby channel. We've got the tips archive up and running, so you can sort these by different types of tips, like sort by drawing, and then you'll only see the tips that have to do with drawing, or sort by eventually sheet metal. We'll have that as well. So the different tips here can be sorted based on what type of a tip it is. But also remember that at TooTallToby.com, we've got the leaderboard up and running. And from the leaderboard here, you can click on people's videos. Looks like Airwick came in, swooped in, and beat Victor's time. So now Victor's going to try and swoop in and beat his time. You got different CAD systems. So this guy, Juiced, is using ANSYS Space Claim. So if you want to watch a different CAD system and see how it does this speed run, you can just click on this link here and watch his video. Airwick, I'll get your video updated today. But yeah, you can go and you can see different CAD runners using different CAD systems and trying to run this challenge. And if you want to take the challenge yourself, just click this button that says compete. The clock is built right in. You can try to build these 3 models using the drawings that are right here at this 2D drawings link, and you can try to build them yourself and see what kind of a time you can come up with on that leaderboard. And I think that is a good place to say goodbye to everybody. So thank you all so much for joining us today, and have a good rest of the week. I will see everybody soon. Bye, everybody.